Good afternoon, everyone. Good morning, or good, in the West Coast. Good afternoon in Europe, and good afternoon in the US. So welcome, everyone, to this first search and matching in macro and finance workshop. Today's theme is discrimination in the labor markets. We have, excellent 5-paper program this afternoon. And there are the papers consist of a combination of theory, evidence, empirical analysis, lab experiments, and so on. So we hope to have a very fruitful discussion on an important topic that's capturing the attention of public policymakers, and so on. So let me turn over to the real organizers of the conference, Zach, Shenxing, and Lucas, for them to make a brief remark.
Hello, everybody. Thank you for joining. So I'll talk a little bit about the format. So first things first, there's going to be a video recording on our website. The way this works is that we have a group of panelists, which consists of all the authors and co-authors of the papers on the program today, and they will be able to interrupt the presentation and ask questions to get a lively discussion going. But we really want participation from everybody. So please feel free to ask your questions in the Q&A. The co-authors of the papers will be answering the questions live there in the chat. And then after each 30 minutes of presentation, we'll have 10 minutes of Q&A where we will be inviting you guys to raise your hands using the Zoom feature to raise your hand. And then we'll be taking audience questions as well. And I think that's all I have to say. So it's really time for Peter to take it away now.
Okay, thank you. So you see my slides? Okay, great. So this is joint work with Jiadong Gu, who is, I think, will answer questions in the Q&A, and he's a grad student at UNC. So I'm gonna keep the motivating part short here. So I just wanna, there are several ways to motivate our paper, but one way is that there is lots of evidence that the gender gap is somehow accounted for by occupational choice. And this has several interpretations, one of them being that women may care more about amenities, so that non-wage properties of the job. Another interpretation is that maybe women accept low-skilled jobs because they have underconfidence or their higher level of risk aversion or other sort of preference-based explanations. So this paper offers an alternative view of how the gender gap could account for lots of the wage differences. So we're gonna assume away all these potential differences in preferences, and instead we're gonna construct equilibria in which women are overrepresented in low-paying jobs. Now, because we're looking at the symmetric model, it will be the case that there are also equilibria in which the role of the groups is reversed. I don't feel particularly uncomfortable with that because I don't think the theory here needs to explain the initial conditions. Rather, I think what the role, the sort of an important role for theory here is to explain that if we start somewhere for some maybe historic reasons, how can we explain that when, say, barriers to labor participation in some better paying jobs have been removed, how can we explain then that we don't see convergence and a model with multiple equilibria is doing just fine for that, I think. Now, additionally, it's not just a multiple equilibrium story, but our model has something to say about a tendency that it's possible for some parameter ranges that the model almost predicts that we should get asymmetric equilibria because symmetric equilibria may not be stable once we introduce the group characteristic. So I'm going to be incredibly brief on how this relates to the literature, but the way to think about the paper is that we take the standard logic from mainly static models to statistical discrimination, and then combine that logic, which has to do with self-confirming prophecies, with a search model. And the role of the search model is that the search externalities is going to combine with the self-confirming prophecy in what we believe is an interesting way. So we should note that unlike models of statistical discrimination, we're going to assume away any endogenous human capital investments. So we don't gonna need any equilibrium scale differences. And the way we're gonna be able to account for the wage gap is that there's more mismatch between between women and good jobs than between men and good jobs. So the equilibrium sort of looks like as if women are sticking to low paying jobs because they're underconfident, but there is an equilibrium logic that explains that behavior. So to be very clear, the combination of the statistical discrimination with search means that we do have this self-fulfilling prophecy part from that is just like a standard model of statistical discrimination, but then this is combined with the search model to create what we think are interesting cross-group spillover effects that in this model works via firm entry decisions. So just to be very clear, the self-confirming fulfilling prophecy part is just if we assume that skilled women are less likely to accept more likely to accept low-paying jobs, then skilled women are going to flow out of the pool of unemployed faster than skilled men. So if you then look at the pool of unemployed, a woman in the pool of unemployed is going to be less likely to be skilled, even though their proportions in the population are the same. Combine that with an information problem. So the information problem we have in mind is that you don't know, you cannot exactly observe how skilled the worker is. Then what the firms need to do is that they need to form probabilistic beliefs over whether a worker is skilled or not. And by then just applying Bayes' rule, a woman given a particular noisy signal of their skill, and a woman will need a better noisy skill test or a better interview than a man. So what happens is that they're going to be less likely to get the good jobs, which then reinforces the initial guess that skilled women are more likely to go into low-end jobs. So we get this self-fulfilling prophecy part of the model going, which is very, very much like the standard literature on statistical discrimination. What we need the model for is to explain how this self-fulfilling prophecy combines with the firm entry decisions to create these cross-group effects, which we think is the interesting contribution of the paper. So to explain the mechanism, I need to explain a little bit about the model, and I'm going to start off doing this in the symmetric model where I have not yet introduced the group characteristic. So except for the informational part of the model, our goal is not to make the model realistic, but rather our goal is to make the model as simple as possible. So we're going to look at an infinite horizon, discrete time, and I'm going to have a unit mass of workers. Now, a proportion of them are going to be what we call qualified, and the rest of the workers are not going to be qualified. So there are going to be two kinds of firms. They're going to be firms that I call low tech. And what is special about, or these firms are just going to be sort of noise in the model, really, because what they're going to do is that they're going to want to hire any worker, because any worker is going to be equally productive when matched with a low tech firm. High tech firms, in contrast, have a technology so that only qualified workers are productive when hired by a high-tech firm. So if you look at this little matrix here, I'm going to assume that wages are exogenous. So that means that if a qualified worker is matched with a high-tech firm, then the qualified worker gets a higher wage. The WH is going to be larger than WL, so everyone likes to work in a high-tech firm. And also the high-tech firm is going to make a profit. However, if an unqualified worker is matched with a high-tech firm, then the worker is going to be happy because the worker earns a high wage, but the high-tech firm makes a loss. In contrast, in a low-tech firm, it doesn't matter for the firm whether it's a qualified or an unqualified worker, they're all going to make a profit. And I'm going to assume that the profit from a qualified worker matched with a high-tech firm, that profit is going to be strictly larger than the profit for a generic worker with a low-tech firm, so that I can get entry into the high-tech sector. So the information technology is sort of off-the-shelf statistical discrimination model. So the firms cannot directly observe if a worker is qualified, but there is this noisy signal that's available. It's going to be without loss because this signal is just information. I can order the signal so that we have one conditional distribution given that you're qualified, another conditional distribution for unqualified, and signals are going to be ordered so that the likelihood ratio is strictly increasing. That means that the higher the signal, the more likely the worker is going to be qualified, and that's going to be true regardless of, it's going to be true for any interior prior distribution, which is nice because the hiring rules are then going to just be threshold rules. And here comes a bit where there could be some confusion. So I'm going to assume random search. And not only that, I'm going to try to make the matching technology as simple as I possibly can. So the way I do that is that we're going to assume that the short side of the market is matching for sure. So there's going to be entry of firms. So in equilibrium, it's going to be the case that we have more firms on the market than we have workers, which means that workers are going to match with one firm in every period. But there's going to be entry into the low-tech sector and to the high-tech sector. So because of this simple matching technology, from the worker point of view, what's going to matter is the proportion of firms that enter into the high-tech sector and the proportion of the low-tech firm. So P is going to be important variable. That's going to be the proportion of high-tech entrants. So by the way, feel free to interrupt if there are clarifying or other important questions. Then in order to be able to think, to have some steady state conditions work, we need separations. And we just assume that separations are exogenous. So we're going to have the same separation rate in all matches, except when an unqualified worker is matched with a high-tech firm, in which case we allow that there's a higher separation rate than for the other matches. The idea here is that, well, so we allow for the high-tech firm to discover that it's a bad match, and then they may want to fire the worker, which is not crucial for the logic, but it's actually useful in some of our examples. So what's the equilibrium problem here? So in the pool of unemployed, there's going to be some endogenously defined, endogenously determined proportion of unemployed. I call that pi. From the point of view of optimal firm hiring, this pi is going to generate conditional on meeting. If a high-tech firm is meeting a worker, this is going to determine a unique threshold, called that S of pi, so that the firm is going to hire the worker if the noisy signal exceeds that threshold. Low-tech firms are uninteresting here. They just make offers to anyone. But the rest of the equilibrium determination is going to be where we're going to have to figure out what the entry in the two sectors are. And we also going to have to figure out whether a qualified worker is going to accept an offer from a low-tech firm. And that's going to be part of sort of a static fixed point problem. So we take pi and S of pi as given. Then we're going to determine P of pi, the proportion of high-tech entrants, and alpha pi, the probability that you accept a low-tech offer, as a static part of the fixed point problem. And once we have all these, the pi, the S of pi, the alpha pi, P of pi, then through the steady state condition, that's going to generate a new proportion of unemployed. And then we just run through this. So we just determine, get a fixed point, sort of a dynamic fixed point problem in pi from this. There's going to be a slight caveat on that I may not have time to talk about. And in terms of the firm incentives, the firm has the most standard conditional on being matched with either a qualified or an unqualified worker. The value function, if you know that, is kind of the simplest value function you could imagine in search. And then also adding free entry, that means that once you separate, the value is 0. What that means is that the value of being either matched with either a qualified worker or an unqualified worker is determined purely in terms of exogenous parameters of the model. So WU, that's your combination payoff from matching with an unqualified, that's a negative number. WQ, that's the combination payoff matching with a qualified, that's a positive number. And from this point on, we can take these as the parameters of the model. And what I already said most of this, that, well, so now if you're a high-tech firm, you just need to determine the threshold probability that the worker is qualified. That makes you indifferent between hiring the worker and not hiring the worker. That's your S of pi. And that's
Peter,
it. Yeah.
sorry to interrupt. Hamming has a clarifying question.
Okay.
Sorry, so just I guess you assume that the only thing the firms observe of the worker when they make the decisions is the test signal, right? There are other possible information regarding the employment duration, for example,
Yes,
or the past signals that the worker might have received are not observed by the current firm, right?
That's all correct. So I'm assuming that the signal is the only thing you see at this point. Now, later on, I'm going to assume that signal and whether you're a man or a woman is the only thing I see. So there are interesting things you can do. And there is this paper by Jarouche and Philosoph, where there's statistical discrimination based on unemployment duration, but I want this model to be simple, okay?
Okay.
So now, in terms of the entry, well, so we can run through, we're gonna, for the same reasons as for the high-tech firm, the continuation payoff for a low-tech firm to hire any worker is just gonna be a number that's gonna be a positive number. So then, given that K is the cost of maintaining a vacancy, then the free entry condition is gonna be equalizing that K with the present value of the expected profit from what could happen in the next period, which is some probability PF, that's the probability that I'm matching from the point of view of the firm, times the expected continuation payoff if you're in the high-tech sector, or the expected continuation payoff if you're in the low-tech sector. The reason why I put this up here is that what you say is that this P sub F is gonna have to adjust in equilibrium to account for differences in various endogenous payoffs. But what has to be true, if both sectors are active, I get an indifference condition, which is the condition that I have on the bottom here. And this indifference condition is gonna be what's important for the rest of the analysis, because and that indifference condition, I can just ignore the market tightness variable PF. So to summarize optimal entry decisions, there's going to be, if there are very few qualified workers, then we only going to get entry in the low-tech sector. If there are very many, if most workers are qualified, we're only going to get entry in the high-tech sector. And then in between these two threshold values, pi lower bar, pi upper bar, we're going to have coexistence of the two sectors. And the interesting analysis in the model is when we have the two sectors being active. I don't really have time to get into the value function for the workers, but the only decision is going to be, are you accepting a low-tech? If you're qualified, will you accept a low-tech job or not? For that decision, there's going to be a threshold probability of getting a high-tech offer in the next period that's going to matter. So that total probability, if is going to depend on firm entry into the high-tech sector, and this AQ of pi, which is the probability that conditional on meeting with a firm in the high-tech sector that I'm getting an offer. And this is determined uniquely from this unique threshold S pi that I talked about before. So that's what I'm gonna tell you about the workers. Then there are gonna be some input-output BAF type conditions. So we have 4 of them. And what we can do is that we can collapse these 4 inflow-outflow conditions into a single steady state condition for the symmetric model. And we can just run through these steady state conditions, and we can show existence of equilibrium. Right. Yes.
Hi, this is Ini. So I have a clarifying question. Yes. So is there a single pool for each group, or is there a common labor pool?
So can I answer that question in a second when I go to the 2-group model?
Yeah, thank you.
Okay. So just to summarize, we have the interesting part of the here is between P lower bar, P upper bar. So in between these numbers and at P lower bar and P upper bar, we do have coexistence. We have both sectors, entry in both sectors. And then we can have equilibria at P lower bar and P upper bar, which are pure strategy equilibria from the point of view of what the workers are doing. But in everything in between, we have to have the worker being randomizing between accepting and rejecting offers from the low-tech sector. So now going to Yingni's questions. So now we're gonna add this observable group characteristics. So you can be a man or a woman, and that's the only change in the model. And to answer your question, we're not gonna have separate markets for men and women. If we were to have separate markets for men and women, this would be a very different model. And in fact, most of the interesting characteristics of the model would go away, because the only way we could get multiple equilibria with discrimination then would be sort of like in a Codon-Lowry type model, where men would be coordinating on a good equilibrium and women on a bad equilibrium. That's not what we want to do here. So
Peter, so you have 5 more minutes.
okay.
Yep.
So there's going to be some proportion of workers from each group. I'm going to denote that by lambda. And as you probably understand, there's going to be symmetric equilibrium. We're not interested in the symmetric equilibrium. We're interested in the asymmetric equilibrium. And in terms of how it works, the hiring rules are going to be separable, because when we have conditional on a meeting, all we care about is the profit from this match, which means that the hiring is going to be just like in the model with the single group. What's going to be different compared to the model with the single group is that the condition for when for whether I'm going to accept a low-tech job or not, that's going to be determined by this total probability of getting a job offer in the next period from a high-tech firm. This total probability is going to be the product of the probability that I'm running into a firm which is high-tech, which is this P of pi. But P of pi, that doesn't only depend on what my own group is doing. So this is, I presume, why Yingni asked the question. So the entry into the sector is determined by just by an indifference condition that is determined by the proportion of qualified in each group. So what that means, which is an important insight, is that because we have to the probability that we're meeting a high-tech firm is the same for both groups. If we have the slightest difference in the proportion of being qualified, we cannot have both groups being randomizing. So if men have a slightly higher chance, if they're just a tiny bit more likely to be qualified in the pool of unemployed than women, it has to be that either the men are rejecting low-tech offers for sure and women are randomizing, or men are randomizing and women accept for sure. In each case, once you run that through the steady state condition, a tiny little difference in what in group behavior would be blown up into a big difference once you run through the steady state dynamic. So that means that fully mixed symmetric equilibria are non-robust in the model. Now, let me, how many minutes? I have 2 or 3 minutes or something?
2 minutes.
Okay, let me, so we have a proposition here, which is a theoretical claim that if we have a certain mixed strategy, fully mixed equilibria, then we can, there also exists asymmetric equilibria. And what's important about this result is that this proposition does not require existence of multiple equilibria in the single group model. So we have multiple equilibria in the group, asymmetric equilibria with the group identity that pop up even when we have unique equilibria in the symmetric model. Let me try to, instead of talking about that, going through a numerical example. So what this blue line here is, that's running through the steady state logic. So what you see here is that in this numerical example, we have there's no candidate equilibria except possibly at this pi lower bar and pi upper bar, where we have the workers are either rejecting or accepting low-tech job offers for sure. Now, that part of the steady state equation we cannot look at in this as a function of pi, but then we just have what's going to be the equilibrating variable at pi lower bar and pi upper bar is just going to be to have firm entry to adjust to satisfy the steady state condition. And we can find such firm entry probabilities. What you can't see in the picture is that when we do that, the value of P on the left-hand side at pi lower bar is consistent with rejecting a low-tech jobs and an equilibrium, but the other is not. So this is an example where where we have a unique symmetric equilibrium. Now, in this very example with a unique symmetric equilibrium, let's just guess that women are randomizing. If I do that guess, I can nail what the entry probability have to be, this entry probability that, this proportion of high-tech entrants that make women indifferent. I also then, given that entry decision, just gonna guess that men reject the low-tech job. And if I'm just then plugging this into the steady state conditions that are remain once I made these guesses, this is the picture that I get. And what you see then is that where the red line intersect with the blue line, then we have, given these conjectures, the steady state conditions for both men and women being satisfied. So this is then an explicit example of a parametric version of the model in which we have a symmetric equilibrium, but where we have an equilibrium where men are reject the low-tech job and women are indifferent between rejecting. In this equilibrium, men are better off than women, and everything comes from this just differences in whether you what you do when you get low-end job. So I'm gonna have to finish up. Turns out that affirmative action is actually, given this problem, an efficient tool. I don't have time to explain that, but I'm just gonna conclude by saying that what the model shows in the context of the gender gap and occupation choice is that it can very well be that a gender gap associated with differences in occupational choice could be driven by discrimination in the labor market as opposed to any sort of differences in preferences. So thank you. Lucas, I'm done.
Thank you, but why are you looking at me? Sheng is moderating your talk.
Oh, so there is a question from the audience, Errol, that basically The question is what, I guess the gist of the question is whether you are talking about basically a random matching within a sector, or does the model also apply to maybe job search across different sectors or occupation? I guess.
Well, so there are two occupations in this model. So there is what I label as the high-tech sector, which has sort of cushy jobs, and there are other jobs. There are the low-tech sector where skills don't matter. And we have a very, very simple matching technology where we are assuming that both these sectors are running into workers in accordance to in accordance to the proportion of jobs in each sector. That's clearly a simplification, but there's nothing in the logic of the model that would change if, say, the high-tech sector would be better at finding job candidates than the low-tech sector. So that's not important for the logic. So I'm not sure whether that addresses the question, but there are search externalities that in this model that are driven by them sharing all the same market, but the rates of matching could be different.
Randy has another question.
Can you hear me?
Yep.
Peter, we discussed this before, but I'll mention it again because not everybody in the audience today was privy to that. I think it'd be really nice to endogenize wages here. As I understand it, you're still working in the fixed wage case. The reason, so discrimination is thought by some people to be an example of the failure of equilibrium, that is the price mechanism, to deliver efficient results. It's a less interesting example when prices are not allowed to do their job. I think you can get it such that the main results will continue to hold, but it will be still, useful and nice to do it, somehow get wages into the system.
Thank you, Randy. I mean, I agree with everything you're saying, and I've been starting to work on it. I'm just not done. I think you're right that everything is gonna work out mostly the same. Not for every way we can endogenize the wages, but there are ways to endogenize wages that are sensible that we could make it work. I'm just not done with that yet.
Okay.
Peter,
I'd like to ask a question.
Okay.
Because the pool of unemployed is so important in your model, does this also work if there's on-the-job search?
Yes. So, on-the-job search would be fine as long as it's not, it wouldn't work if the matching probability from being unemployed is the same as the matching probability being unemployed. Then the whole thing would just collapse because you'd always just take a job waiting until you get a better job offer. But as long as it's more efficient to search while being unemployed, this is going to continue to work.
So I guess the question is, okay, you imagine you have a woman who's very high skilled at programming, but she's stuck in a job as a waiter. Well, what's stopping her from applying to tech jobs while she's being a waiter?
No, I agree with that, but what we need for this to work is that it's harder for the woman stuck as a waiter to get the tech jobs than for somebody who is devoting all their energy into searching for jobs.
All right, thank you.
Peter, can I just make a quick comment? One is, the model, the firm's hiring decisions is a threshold signal, but but the model has implications regarding the average productivity of male or female workers hired on a technical high tech job, right? So on the margin, of course, everyone the marginal male and female worker are equally productive for the firm, but the average may be different. I think it will be useful to flesh out some more testable implications for the model regarding average productivity at different sectors by gender. The second comment is about, you take the information structure as given. You said off the shelf, a Colton-Lowry style information structure. Have you thought about actually bringing in information design into this problem, where the signal itself, testing technology itself could be something that the firms can be, designing to deal with any information problem that the firm faces regarding workers type?
So I'm gonna start with the second question. Yes, we have thought about that. We don't have a satisfactory model of it yet. The hard part is you sort of have to, in not too cheap a way, I think, explain why why more information is just not better. So, I mean, maybe some cost of the signal would be a cheap way to do that, but I think it would be nice if one could do some sort of serious persuasion. We haven't done that yet successfully. And your comments about the testable implications are well taken. My hunch is that the relative productivities in the high-tech sector could go either way. And that would depend on sort of local properties of the signal distributions. But maybe if one would be to making assumptions about some convexity or concavity, one could get something. But it's well taken, that point. Any other questions?
I guess we are running out of time. If there are more questions, we can continue talking during the coffee break. Yeah,
obviously, everybody, the Q&A stays live. So if you have questions in the Q&A that relate to Peter's paper, Peter can answer them in the Q&A himself.
Okay, great. So I should start share now, right?
Yes.
Okay, let's move on with the program then. And we're so excited to have Aizen as our next presenter. Take it away.
Let me just get my slides ready here. Let's see.
All right, while that, I just wanted to tell everybody we are now in the process of putting slides up to the workshop website as well. Aizen's slides are already there.
Okay, can everybody see these slides?
Yep.
All right, thank you so much for hosting this today and inviting us to be as part of the panel. My co-author Alex Emos is on as well, so if you have questions, clarifying questions that you want to pop in the chat, feel free to do so. He's happy to answer them. Also, feel free to interrupt me. So this is joint work with Kareem Hagag, Alex, as I just mentioned, and Devin Pope. And today we're going to talk about a potential identification problem and in trying to identify what is the underlying source or cause of discrimination. So we know from the empirical literature on discrimination within economics that systemic discrimination has been well documented. We've seen discrimination along the lines of racial, ethnic, gender, sexual orientation. We've seen this documented in a variety of important markets, such as housing markets, credit, labor markets, or online consumer markets. Han Meng has a very nice overview of this work, as well as a Bertrand and Duflo paper. And so when we look to this literature, in general, there's two potential sources of discrimination or causes of discrimination that are positive. The first goes back to the classic paper by Becker in 1957, which is discrimination is what we call taste or preference based, in the sense that it's due to animus or dislike for members of a particular group. This contrasts with what we call statistical discrimination, as we saw in the previous talk, which is going to be due to some sort of uncertainty about the characteristic of, say, the worker or the person being evaluated. So perhaps this is because people believe that one group's average productivity is lower, as modeled in Phelps and Arrow. Perhaps it's because people believe that one group has higher variance than the other, as modeled in Igner and Kane. But either way, sort of the key difference here is that the first condition is based on preferences, whereas the second condition is based on beliefs. So distinguishing between these two types of discrimination is important for policy and welfare. Often a method used to do so is what's called the outcome-based test, which is to compare the actual decisions or the actual evaluations for members of each group to the outcomes of that group and see whether those decisions match those outcome distributions or see whether they differ. So this is one way that we could identify source. I'll discuss a little, or I'll get more into the details of this in a few minutes. But one thing I want to point out is that a key identifying assumption of this method is that beliefs are accurate. So we have statistical discrimination with accurate beliefs, or preference or taste-based discrimination due to preferences against a particular group. So in today's talk, we're going to make the case that we should also consider a third potential source of discrimination, and that is discrimination stemming from inaccurate beliefs. Why are we making this case? Well, there's evidence from psychology and economics that people have systematic biases in their beliefs, things like inaccurate stereotypes based on the representative heuristic, as in Bordallo et al. And there's an enormous literature in psychology discussing how stereotypes can be inaccurate. In other words, they don't reflect the true distributions or the true features of the environment that they're formed about. We can also have inaccurate beliefs, maybe not because of any systematic bias, but just simply from a lack of information. So maybe we're inexperienced. What's the probability aliens arrive from Mars? We don't really know. We've never seen this situation before. Or we could also potentially have accurate priors about population averages. For example, the population or the abilities, say, or the productivities of different groups graduating from university, but we may be unsure how selection impacts that population being evaluated, in the sense that if we're looking at, say, a higher level position within a company, then all of the hiring and promotion criteria up until that position is reached is going to influence the actual populations that we're seeing for each group. And so in other words, if there's discrimination earlier on, that's going to act on the population distributions of ability in a way that's going to change things. And so in order to have correct beliefs at higher order points in the process or the pipeline, we need to really fundamentally understand not only how things started, but how things evolved throughout this whole promotion process. It also requires potentially a knowledge of other people's beliefs. So if we're trying to figure out how to interpret a recommendation letter, we not only need to see what is that letter actually saying, but we need some sort of, it's subjective, and so we need some sort of belief about the person writing the letter. How subjective are they? Are they potentially discriminatory? How good are they at evaluating different workers? So as you can see, having accurate beliefs is much more complicated than just potentially knowing what the population means are for different groups. So why does this matter for discrimination? Well, if evaluators are trying to learn about the trait of a particular candidate, then their beliefs about all these different features, the population distributions, how different pieces of information such as GPA or test score convey information, how prior evaluators have evaluated these and so on, are all going to influence the learning process about a particular candidate. We know from the theoretical literature, most recently on model misspecification, but also going back on behavioral models of learning, that inaccurate beliefs are going to lead to inaccurate inference. And importantly, this may persist even in the face of a lot of information about the candidate. So we see from the model misspecification literature, we can have settings where in the long run, even if there's sufficient information to accurately learn a candidate's trait, evaluators may converge to having incorrect beliefs about that trait if they're not processing information correctly. It can also cause inefficient exit from the market. So even if learning would be correct, if it was allowed to continue for long enough, inaccurate beliefs can cause people to inefficiently exit if they're not promoted, say, relative to their colleagues who are viewed more positively. In the companion paper Alex and I have with Michael Rosenberg, we demonstrate how these the dynamic process of discrimination really can fundamentally depend on whether people's beliefs are correct or incorrect. All right, so in today's paper, we're going to argue that it's important to distinguish between discrimination due to accurate versus inaccurate beliefs, both for a methodological reason. Importantly, relaxing the assumption of accurate beliefs is going to generate an identification problem, as we'll show in our theoretical model. And then also from a policy perspective, if we're interested in trying to, say, reduce discrimination or disparate treatment based on group, then effective interventions when beliefs are inaccurate are going to be very different than those for either accurate statistical beliefs or taste-based sources. Additionally, the welfare implications for inaccurate statistical discrimination differ from the welfare implications for the other two cases as well. And so we want to try and evaluate the welfare of a given hiring setting with discrimination. We really also need to understand what is generating the discrimination. All right, so as a first step, we view this sort of mostly as a conceptual paper to really illustrate how inaccurate beliefs could potentially confound identifying the source of discrimination. And with the point being that this is important because a lot of the literature in discrimination really hasn't focused on the possibility that beliefs may be inaccurate. So as a first step to document that, we looked at the literature in discrimination over the past 30 years or so in order to get a sense of how many papers did allow for the possibility of inaccurate beliefs. So we looked at a list of 10 different journals. We looked at papers from 1990 to 2018, empirical papers that tried to document discrimination or disparate treatment based on some group identity. So within our inclusion criteria, which I don't have time to go through in more detail today, but you can find in our paper, we found 105 papers that met this criteria. Within that, 102 of them found evidence of discrimination. 65 of them, or roughly 62%, at least discussed the difference between taste-based and statistical sources, so tried to say something about the source. 46% of them tried to actually distinguish between the two. So, of course, documenting discrimination in the first place is important. It is, in general, even with accurate beliefs, difficult and not possible in all settings to distinguish the source. So that's why, even though people are very much aware that there's different sources, not all papers that document discrimination have a way to actually distinguish these sources. So roughly 47% did. But when we try and see what happened with accurate versus inaccurate beliefs, only 11 papers, or 10.5% of these papers, discussed that there could be inaccurate beliefs. And 7 papers either tested for inaccurate beliefs or measured beliefs to try and get a sense of what people's beliefs actually were when they were making these decisions. So as you can see, it's sort of more recently, I think, to a couple of the theoretical literature looking at inaccurate beliefs, the discrimination literature has started to discuss inaccurate beliefs. But as we can see, there really is sort of a lot still to be answered in terms of how inaccurate beliefs may potentially generate discrimination and how different interventions would respond to settings in which there's inaccurate beliefs versus settings in which there's either accurate statistical discrimination or some sort of animus against the group. All right, so I'm going to start with a simple theory model to illustrate why we potentially have an identification problem when we allow for the possibility of inaccurate beliefs. So let's suppose there's a worker. The worker has some group identity, M or F. The worker has some hidden productivity, A, which is normally distributed with a group-specific mean mu and a precision, group-specific precision, tau. And the worker generates some signal, which is essentially the worker's productivity plus a mean zero error. So the error has precision eta, a group-specific precision eta, and we could think of this as there's some underlying productivity and something like an SAT score or GPA is going to convey information about that productivity. Just in order to keep things consistent, we're going to focus on discrimination against group F. And so what happens for this worker? This worker presents him or herself to an evaluator, and this evaluator decides whether or not to hire the worker. So B equals 1 corresponds to hire, B equals 0 corresponds to do not hire. The worker holds subjective beliefs about the distribution of productivity for each group, as well as the informativeness or the precision of the signal for each group. And here in our theoretical framework, inaccurate beliefs, or what we would in theory call a misspecified model, occurs when the subjective parameters about the distribution of ability and the signal differ from those true parameters. So there's a variety of reasons why this could arise. There's models that look at, say, providing foundations for this reduced form of inaccurate beliefs in terms of things like only observing information from peers in your network and forming beliefs based on an imperfect sample that you don't understand, so on and so forth. That's all really what comes into play in the theory literature on the specification. For today's talk, we're going to take this as given and just refer someone who's interested to the large literature in both psychology and theory that explores where these inaccurate beliefs may potentially come Okay, so given these beliefs, the evaluator observes the worker's group identity and the signal and uses Bayes' rule to update her belief about the ability of the worker. And then she hires the worker if her subjective posterior belief is above a group-specific hiring threshold, UG, where we take this as a reduced form for some underlying payoff relating how the evaluator cares about the worker's ability. Right, so importantly, this group-specific hiring threshold captures the evaluator's preferences. If these hiring thresholds differ, that means the evaluator potentially has different preferences over the two different workers. So this preference parameter UG, as well as the evaluator's beliefs for each group, denote the evaluator's type. We define several different categories of preferences and beliefs, which we refer to as partiality. We use this term partiality to refer to properties of the model primitives. We want to distinguish it from discrimination, which is a property of behavior and a consequence of those primitives. And so when we say things like taste-based discrimination, what we're going to mean in the context of our framework is discrimination arising from these partiality conditions on the underlying preferences and beliefs that are suggestive of a taste-based or a preference source. So preference partiality, an evaluator has preference partiality if their group-specific hiring thresholds differ, UF is not equal to UM. We say that discrimination is taste-based if it's caused by these different preference parameters. Similarly, belief partiality corresponds to an evaluator who has different beliefs about some or all of the different underlying subjective parameters for the two groups. And again, we say discrimination is belief-based or statistical if it stems from primitives where the beliefs differ for the different groups. This belief partiality is accurate if the beliefs are equal to the true distributions, and otherwise it is inaccurate. All right, so then taking this to discrimination, letting V of SG theta denote the optimal hiring decision. In other words, this is equal to 1 if the posterior belief about ability, given the evaluator's model, is above the evaluator's preference parameter UG. Otherwise, a worker is not hired, and this is equal to 0. And so letting D of S theta denote the difference between the hiring decisions for a worker from group M and a worker from group F who have the same signal S. So importantly, in order to document differences, we're holding fixed the signal in order to compare essentially the same quality or the same performance from a worker. The only thing that differs is their group identity. And we say discrimination occurs against the worker from group F if there exists a signal such that D of S theta is greater than 0. So in other words, a signal at which the male would be hired, that worker M would be hired, but worker F would not be hired. And so as a first pass in trying to figure out how we can identify the source, we're interested in when the same sets of beliefs and preferences give rise to the same or indistinguishable discriminatory behavior. So we say two evaluators of type theta and theta prime exhibit equivalent discrimination if D of S theta is equal to D of S theta prime for all possible signal realizations. In other words, regardless of what generates that behavior or those hiring decisions, the hiring decisions are the same for all signals that those workers would generate. All right, so given that the posterior mean about ability is monotonic with respect to the signal, we can represent the optimal hiring decision as a cutoff rule with respect to the signal. The worker is hired if their signal is above some group-specific threshold S bar that depends on the evaluator's type as well as the group. And so given this, we can say that two evaluators, if two types have the same signal cutoffs, that means that these two types exhibit equivalent discrimination. So we have an analytical result characterizing the set of types that exhibit equivalent discrimination. I think it's a little easier to explain in the following figure. And so what we do here is plot what we call isodiscrimination curves. So an isodiscrimination curve, just like an indifference curve from Econ 101, is essentially a curve on which for any preference parameter U, as well as any beliefs about each of the different components of the worker's productivity distribution and signal distribution, evaluators on that isodiscrimination curve, their beliefs and preferences may differ, but they exhibit the same discrimination. So here I have isodiscrimination curves plotted in 2 dimensions. On the x-axis, we have the evaluator's belief about average ability for group F, mu hat F. We have the hiring threshold UF, that's the preference parameter. And any discrimination or any point along this line, of course, since it's 2 dimensions, we're holding fixed the other parameters. Any point along this line is going to lead to the same discriminatory behavior against group F for the evaluator type. So coming down here, we have a point, the red line corresponds to the line of no discrimination. As we move in the northwest direction away from that red line, we're moving to regions of increasing discrimination. And then also here we can outline different particular types we're maybe interested in. So here the belief for—
Excuse me, could you clarify what the significance of the number 5 is? Is that the belief about the ability of M?
Sorry, could I clarify the significance?
So what's the significance of the number 5 here for the green line?
Oh, that's about what I was about.
Does that mean that's the belief in the ability of M?
Here we have the line of belief neutrality. What this corresponds to is the belief about average ability for group M is 5.
Okay, thank you.
And so if the belief about average ability for group F is also 5, we're on the line of belief neutrality with respect to average productivity, so mean productivity is this here. Similarly, the line of preference neutrality, well, UM is equal to 6 in this curve. I should have put the parameters below here, but UM is equal to 6. And so if UF is also equal to 6, then we're in a setting with preference neutrality. In other words, there's no difference in preferences between the 2 groups. So as we can see, this isodiscrimination curve has an evaluator type with belief neutrality. It has an evaluator type with preference neutrality. It has types that exhibit both preference and belief neutrality, both preference and belief partiality against group F in this quadrant right here. There can also be types who say, for example, have belief partiality against group F, but it's somewhat tempered by preference partiality in favor of group F. So maybe you think one group is, say, worse than the other, but you also want to try and help that group, and so you sort of favor them by setting a lower threshold. That would be types over in this region. Okay, so we're going to use this framework of the isodiscrimination curve to go through and see what we can do to try and identify the source of discrimination, or in other words, a particular type for the evaluator. All right, so can a property of interest be backed out from available data? We're going to assume at a minimum that the researcher observes the group and the hiring decision for each worker, and we're going to explore what else needs to be observed in order to try and figure out the evaluator's type. All right, so the existence of discrimination just as a benchmark, that just corresponds to showing that there exists a signal such that the workers are treated differently. D of S theta is greater than 0 if we want discrimination against group F. If the researcher also observes the signal, this is straightforward. But this isn't necessary. It's well known in the literature that either a correspondence or audit study in which you create fictitious workers and randomly assign them both a group identity as well as a signal is able to identify whether discrimination exists. So these observations just simply say, as long as you can do so for a sufficiently rich set of workers, that you're going to include some workers with signals in the region where discrimination with the hiring rule will differ, that would identify existence. If you want to identify something a little bit stronger, if you want to try and pin down not only that you're in this region above and to the northwest of the red line, but also you want to have a better sense of where you are, so sort of measure the extent of discrimination, then observing this data for a continuum of signals, or sort of very close to a really rich set of signals around the different hiring thresholds will both identify existence as well as which isodiscrimination curve you are on. Okay, so more importantly, in this paper, we're interested in identifying the source of discrimination. And so this is the form of partiality that's going to generate the observed discriminatory behavior. So Lucas, what time do I have until?
We started 5 minutes late, so let's say, sorry, that's a lot of math right now.
So 2:15.
Yes.
Okay. Okay, so the source of discrimination, it's well known that correspondence studies can't distinguish between preference partiality and accurate belief partiality, and this same insight extends to inaccurate belief partiality. Moreover, we show that it's not even possible to rule out any of the potential sources. And we do this by constructing the evaluator types with a single category of preference or a single form of belief partiality, and showing that there's a type that exhibits discrimination that just has preference partiality. There's a type that just has belief partiality in the form of differential means. There's a type that just has belief partiality in the form of differential precisions about beliefs about the precision of ability or concentration of ability. And finally, different beliefs about the signal distribution that can all generate equivalent discrimination. And so what this tells us is that each form of partiality and isolation can generate a given pattern of discrimination. And therefore, even if we can observe the isodiscrimination curve, we can't necessarily figure out anything about the evaluator's type from that. So we have an analytical result. I'm going to do, yep.
Aizling, can I ask a question?
Mm-hmm.
So, you know, when you talk about identification, right? So you typically would like to describe exactly what data you have access to. So you describe the data set being the decision up to now, seems like, you know, the evaluator's decisions and maybe group identity, maybe even signal. But what about outcomes? You know, after maybe you'll be bringing them in, but I thought.
So I'm going to bring that in a minute. So we started by assuming sort of at a minimum, to say anything interesting, you need to observe the workers' group identity and the evaluation. So whether or not they're hired.
Okay.
Then for existence, we brought in if you can observe the signal or potentially observe it by using a correspondence or audit study, creating fictitious workers, and then essentially making sure the signal distributions are the same for those workers. That's going to be quite similar to just observing the signal directly. In that case, that will give you existence. So now we're sort of operating where let's suppose we can identify the isodiscrimination curve. We see we can do that for observing the group, the hiring decision, as well as a sufficiently rich set of signals around the point where the hiring decisions change for each group. And so from that point, we want to see what other data would we need to identify source. So this first part, this is sort of a non-result in the sense that it tells us that if that's all we can observe, then we can't rule out anything. And so we can now think about, let's just be in a world where we're, say, observing the isodiscrimination curve. We know we can identify that from the data I just described. So let's be in that world and let's see what else do we need to add in order to say more about the source. So this is first, this is a negative result in the sense it's really giving us a property of the isodiscrimination curve. It's telling us that any isodiscrimination curve intersects the lines of preference and belief neutrality for all, intersects the line of preference neutrality, and then it intersects the line of belief neutrality for each potential type of belief neutrality. So essentially, each form of partiality we defined in the beginning can generate a given pattern of discrimination. So it's, you know, obviously, if we know we're on this isodiscrimination curve right here, we can say rule out this type right here that's not on the curve. But if we want to say rule out preference neutrality to establish there's at least some animus against the group, observing the isodiscrimination curve doesn't let us do that. And if we want to rule out, say, different beliefs, again, observing the isodiscrimination curve doesn't let us do that. All right, so we're going to need some additional data if we want to try and rule out particular sources of discrimination. All right, so this is just, here we have just one particular isodiscrimination curve from the last graph. This is the set of beliefs about average ability and hiring threshold that lead to the same level of discrimination. Here, as we see, it's intersecting both lines. Those are the red asterisks are the types that just have a single form of partiality. And then over here, we have the same thing. This is actually assuming belief neutrality here, but then taking the belief about the concentration of ability, tau hat F, and showing again, here we have a type with belief neutrality with respect to the concentration. And here we have a type where the given discrimination is just generated by different beliefs about the variance of ability. Okay, we could do the same thing for the signal precision as well.
Hey, Aisling, and now you have 5 minutes.
Yep. I didn't hear your question, Lucas.
No, I just wanted to say that now you have 5 minutes. My bad.
Okay, so let me quickly go through here. So the next thing we want to show is in an outcome-based test, this is a common method to identify source under accurate beliefs. And we're going to show that this is not potentially, this is not going to be a valid method when beliefs may be inaccurate. So what does an outcome-based test do? Well, here beliefs are accurate. Here, if say the true belief about average ability was 4, then we could see this would intersect the isodiscrimination curve at a unique point that would identify this evaluator type right here with accurate belief-based partiality as well as some preference-based partiality as well. 6.8 is above 6, which is the preference neutrality. And so here we can see that if we could additionally observe the outcome data, this is, of course, the true distributions about each group as well as the signal distributions, that would then be used to identify what is generating this discrimination. And so the next thing we show is that this identification crucially depends on the accurate belief assumption. So if the true productivity and signal distributions are identical, differential treatment may stem from preference partiality, inaccurate belief partiality, or some combination of the two. If the true productivity or signal distributions differ, accurate beliefs may be the source, but we won't be able to distinguish it from the other sources just by observing outcome. Right, so here again, returning to that graph, this is depending on the assumption that these accurate beliefs are equal to the true beliefs are equal to the subjective beliefs. Without that assumption, we can still have any point on this isodiscrimination curve. All right, so I'm not going to get into this in the interest of time, but a final thing we could do potentially is elicit beliefs. If we can also collect data on the evaluator's subjective beliefs, then we can use this to pin down the preference parameter and therefore the type. It doesn't identify whether beliefs are accurate, so we would also need to couple this with outcome data if we wanted to say whether discrimination was stemming from a belief-based source and whether that belief-based source was accurate versus inaccurate. Okay, so in the last couple of minutes, I want to go through the empirical part of the paper, which is an experiment that really was an illustrative example to demonstrate how inaccurate beliefs may potentially be generating patterns of discrimination. And importantly, if we don't allow for inaccurate beliefs, then that discrimination due to inaccurate beliefs may be misclassified as discrimination due to a preference-based source. So we look at a simple experiment. I'm not going to spend too much time on the design. Basically, in the first part, we collected a bunch of workers. We had them complete a 50-question math test, as well as answer a couple of questions to make a personal profile. In the second part of the experiment, we had workers who were employers. We showed them the profile of different employees, and we asked them to decide on a wage or a willingness to pay to hire that worker. This decision was consequential. We made it incentive compatible for them to essentially hire the worker because their payoff, if they thought the worker would be a good enough performance, because their payoff depended on the actual number of questions answered correctly. I won't go through the details, but the full design's in the paper for those who are interested. All right, so we looked at 3 sets of group identities in the experiment, Indian versus American, male versus female, and old versus young. For today's talk, we'll just focus on Indian versus American as an illustrative example. And so our first step was to document whether there's differential treatment. Here we have the average wage, or the prediction, on the y-axis. And we see that Indian workers, which are the red line here, were paid a wage that was higher, about $2 higher on average, than American workers, which is the blue line down here. All right, so we see differential treatment. The next thing we want to say is, well, given the conventional pattern for setting discrimination, how would we test for the source of this discrimination? Well, we could compare it to the true performance distributions. We know the true performance distributions here. We can look at those and see whether or not they mirror the wages. So here up here are the dotted lines. This is the average performance of an American worker, and we can see it's slightly above, about half a question above, the average performance of an Indian worker. So from here, if we didn't allow for inaccurate beliefs, we would be done. We conclude that there's case-based discrimination against Americans. They perform slightly better on average, but were paid a lower amount on average, and therefore this must be due to some sort of preference against them. All right, but next we want to say, well, what if beliefs are wrong? So what if making this assumption that people's beliefs are equal to these outcome distributions is not the correct assumption, or is not satisfied? So as the next step, we elicited average beliefs. We asked employers, on average, how many questions do you think each group answered correctly? we made this incentive compatible by giving bonuses for correct answers. And so as a next step, we can see, well, here in the second graph right here, these are the average beliefs about the two different workers. So again, we have our true outcomes or the dotted line. These are the wages. These are the average beliefs. We can see the average beliefs go in the same direction as the average wages. And also we can see here the average beliefs differ from the true outcome distribution. So now with this data, we would then say, well, combined with our outcome distribution, we know that beliefs are inaccurate. And then we see the discrimination over here, the differential treatment of Americans. And so we can conclude that actually this must be generated by these inaccurate beliefs. And so we're seeing inaccurate statistical discrimination against Americans rather than taste-based discrimination. So of course, a natural question is, in the face of inaccurate beliefs, what can we do to correct them? Obviously, this is a very important and question to study in a lot of different contexts, but sort of just within this illustrative example, we wanted to try a simple intervention where we would just say, what if we try and correct people's beliefs by telling them the true average performance for each group? So we told the employers, here are the correct answers for the belief questions you answered. Americans answered on average 37 questions. Indians answered on average 36 questions correctly. And then we, after giving them this information, we again asked them to make wage offers based on an additional set of 10 employee profiles. All right, so here in this third panel right here, we see that the difference in wages did, first of all, it went up for both groups, more in line with the performance, but also the disparate treatment decreased. We see less differences in wages here relative to this first panel before we were given the information intervention. So it did do something, it did affect their beliefs, or potentially at least as measured through their performance, but it didn't quite move things to where the true distribution is. So we see that this is potentially a way to help correct inaccurate beliefs, but just a single signal or a single signal of performance for a subset of a group is not necessarily going to move people all the way to the true outcome distributions. All right, so I'm out of time, so just to take a minute to conclude, we posit that inaccurate beliefs may be prevalent in many domains currently being studied by discrimination researchers. Most tests that try and separate statistical and taste-based sources rely on the assumption that people hold accurate beliefs. Incorrectly imposing this assumption can lead to a mistaken attribution of source and therefore a potentially misguided policy and welfare analysis. Relaxing this assumption of accurate beliefs generates an identification problem. And we give an illustrative example using results from an online experiment to demonstrate the importance of how inaccurate beliefs affects how we study discrimination.
Thank you, Aizen. So I have a question about the last slide. Did you ask them for their beliefs again after you told them the correct number?
No, we did not.
Because I would speculate that they, like most people, shaded their beliefs like halfway, but not fully. All right, let's open it up to questions. So attendees, please, if you would like to ask a question, use the raise hand feature and we will call on you. Ask a question in the Q&A and we can call on you too.
Hi, Aislinn. Hi. I have a question about the decision model, right? So we are assuming that the employer only cares about the expected ability, but how about the variance? Maybe one group is riskier than the other, but even if they have a higher average ability, they still get lower hiring chances and a lower wage. That's still consistent with statistical discrimination.
Yeah, so we just look at, so our, essentially our decision rule to hire or not hire is, we took a reduced form decision rule, but you could think of it as an underlying payoff where the evaluator's payoff is linear in ability, and it has some group specific slope and some group specific intercept, which essentially UG captures both of those. We could, of course, allow for, say, risk aversion over ability or different functions where maybe if a worker is below a certain ability, they're just completely useless to you, or any sort of other payoff functions. We could also look at settings where, say, similar to our other dynamics of discrimination paper, the evaluator is, say, reporting an evaluation like a customer review rather than just a binary hire, don't hire. But so we have a really simple model just to kind of illustrate the main insights in a simple framework, but sort of this key idea that if you don't allow for inaccurate beliefs, then potentially you will misclassify discrimination that's due to inaccurate beliefs as preference-based goes through in a much richer setting. So sort of the key take, the technicalities will be different, but the key qualitative takeaways are similar for a variety of different payoff functions for the evaluator.
So would it help? Sorry. Would it help if you could see a ranking of a number of candidates in order to disentangle things?
So in what sense? Like,
well, so say that you sort of see a firm that rank orders a number of candidates, or first shortlists some candidates and then makes a final choice. Would that help sort of in terms of telling what's preferences and what's not?
No, because so here we're just seeing a binary hiring decision, but in companion work, we look at, say, what if there's some evaluation, like you give the worker, say, a rating from 1 to 10. And so maybe you could think about that as what you're saying. Like, what if you could see a worker's underlying rating, not just whether or not they were above some threshold?
So aren't you already assuming the observation of signals, right? So if you can, in the audit, what's the term, the correspondence audit setting, aren't you assuming already that you observed the exact signal?
Yeah.
Oh, okay, sorry.
Yeah. So I have a separate question. So the English question really seems relevant for your experiment design as well, because employers, I assume that you create incentives so that the hiring the right type of person is consequential, right? It matters for them to hire the people with higher. But we don't, I mean, they may also care about the variance, right? So what's the chance? I don't know, the binary choice, maybe this attitude doesn't matter. So I didn't really think through all that issue. But so I thought that maybe that could be also a factor in the experiment design. So they may not be clear about their perception of how accurate their posterior might be. Maybe we are going beyond the expected utility maximization here, but so. Yeah,
so it would, you know, as I said, this is the experiment sort of a first pass at an illustrative example of how this could arise, but I think, you know, it would be, we didn't elicit their beliefs about the variance, but it would be interesting to also see whether
you can actually document as a result of your experiment that, you know, what their payoff consequences are, you know, as a function of the extent to which they exhibit discrimination. So those that discriminated, I guess, probably suffered more, right?
Well, if they were, you know, if they cared about their expected payment,
right,
then these inaccurate beliefs led to lower payoffs than if they had accurate beliefs.
Right.
So yeah.
Aisling, so nice talk. So you know, conceptually, right, the difference between taste and inaccurate belief is that we, as economists, typically assume preferences are immutable. If you are prejudiced, you remain prejudiced, at least in the time frame you are thinking about. But inaccurate beliefs, you know, can respond to information, can respond to feedback, and so on, right? So I would imagine that these two things are identified if you enrich the data set from a static outcome or static decision to dynamics, right? But then I think even among the inaccurate belief, there is a useful distinction between beliefs that are currently inaccurate, but you are amenable to changes, versus simply stubborn inaccurate beliefs. You refuse to acknowledge anything that you assume being wrong. And right, so in that sense, in that case, it's not clear to me whether there is any distinction between belief inaccuracy resulting in this discriminatory outcome versus prejudice leading to inaccurate outcome, right? So I think maybe if it's an inaccurate belief, but you are willing to update yourself, given the evidence, I think dynamics can help you distinguish that from the taste. But then stubborn beliefs just basically bigotry too. If it's belief, but you are not willing to change anything, to me, that's bigotry as well.
Yeah. Yeah, so I have two thoughts in response to your comments. So the first would be, so indeed, I didn't have time to cover it in the talk today, and it's not in the paper yet just because I'm still working on a couple of details, but we also have a result where it shows that it's called the information manipulation treatment. And it's, instead of eliciting beliefs, as you say, can look at multiple draws of a signal. So for example, you can see 1 customer review or 5, then we can also use that to identify source. So that would be an alternative if there's settings where it's not possible to elicit beliefs, but it is possible to vary information. And that would also be another way to potentially identify whether discrimination is preference-based or belief-based. The important caveat there is that it's not just varying, it's varying information in a particular way. So if we were, say, varying information by showing where someone graduated from university and then also showing their SAT score, those are 2 different signals. And so potentially based on how people interpret, say, if they think there's affirmative action or not, or if they think SAT score is more informative for one group than the other, varying that it can really make things move in a lot of different directions. So it's important that you're taking signals that are draws from the same distribution, or you're making the assumption that the signals are drawn from the same distribution. And so that would make sense if, for example, you're looking at, say, how someone is treated on Airbnb, and we think of their reviews as, it makes sense to think of them as drawn from the same distribution. But yeah, that's a dynamics for sure is, as we have companion work showing, it's a great way to identify discrimination when it's possible. Or the source of. And then the second thing is, so here in our model, it's sort of very easy to say these are beliefs, these are preferences, these are inaccurate. But I think that sort of the underlying conceptual question of what is an inaccurate belief that really is a belief, in the sense that it's something that we can update if we're given information about it, versus these stubborn inaccurate beliefs, which really, for all intents and purposes, might be just like preferences, and sort of formalizing that, or at least conceptually thinking through how to distinguish those 2 things, or how we should really be modeling what we mean by beliefs, I think is, it's a super important question to think about. And often people might, especially now that it's, people have heard of very rarely would probably outright come out and say that they're discriminatory. And so, but they might try and couch it in inaccurate beliefs by saying, oh, well, I believe this, but it's not like they're really beliefs, because if you give them plenty of information to change it, they still wouldn't. They just say, oh, well, that information is not valid, or so on and so forth. And so that's really, that I view as something that, even though the claim may be that people say it's a belief, it's really something more like a preference. Whereas inaccurate beliefs might be something like, okay, I thought that these 2 groups were given equal access to SAT preparatory SAT preps programs. Turns out they weren't. I was wrong. So now I know that, say, this is less informative for the group that had more preparation than the group that had less preparation. So it's sort of that sort of idea, or just not understanding the selection process. If you think a particular group was favored and then you find out you're wrong, or something like that, could really sort of be a belief that people do use that to make their decision, but their beliefs will change in response to information from a good source contradicting it.
Thank you so much, Aislinn. Thank you, everybody, for the discussion. So everybody hates it when this happens at a conference, when the coffee break gets squeezed to 0. But hey, we're on Zoom, so please make sure you're all well caffeinated and have all the drinks you need, because we'll just take a 1-minute breather, and then Sheng Sheng will moderate the next talk. Okay, welcome back from your coffee break. And we're so excited to have Sue present the next paper.
All right, so can you all see my slides and hear me?
Yes, we do.
Okay, great. So first of all, thanks for the organizers, to organize this very interesting, discussion. I think it's a very, timely topic. And also thanks for having me on the panel. So this paper is a joint work with Andrew Morrow from Vanderbilt and also my former student, Bei Zhu. And we got a funding from US Department of Labor. Obviously, the usual disclaimer will apply. So the motivation of the paper is really the empirical research documents a very large and persistent black-white wage gap in the US. But the existence of this wage gap, even conditional on observed productivity characteristics such as education experience, does not provide a direct test for discriminations, even though sometimes people just interpret it as a discrimination, because if there are omitted variables such as observability, which is correlated with education and wage, then this residual difference may overstate discrimination. On the other hand, discrimination, especially pre-mark discrimination, may affect people's choices in human capital investment and other choices. So therefore, the discrimination may understate. So the racial wage gap may understate discrimination, conditional on these group differences. So therefore, it's extremely difficult if we just look at the wage level difference to try to identify discrimination. So therefore, the so-called employee learning statistical discrimination literature try to look at the wage dynamics, basically to look at wage changes over the lifetime to try to identify statistical discrimination. So in this literature, so pioneered by Farber and Gibbons, so they basically argue that employees observe signals of productivity over time, and then they update their beliefs. So this is so-called employee learning. And then later on, Tonjan and Piret, so they use this idea and apply to try to test for statistical discrimination. Basically, employers initially have incomplete information about workers' productivity, and they use group average as a predictor of productivity. So they use employee learning model to test for statistical discrimination. So how do they identify employee learning and statistical discrimination? So the idea is that initially employees have incomplete information at hiring, but then over time they receive signals of productivity. And then at the same time, researchers observe a variable that is correlated with productivity. So in practice, people use FQT as
Suji, sorry to interrupt. So right now we can only still see your title page.
Oh, really?
The case? Yeah.
Oh, I've been.
Maybe it's frozen. You may want to restart the.
Okay, so let me see. I shared my screen. Acrobat. So can you see it now?
Yes.
Okay, so let me. So can you see the new slides?
Yeah, now we can.
All right. Okay, thanks. I thought I was able to share. Okay, so the way to identify employee learning and statistical discrimination is that we observe a variable that is correlated with productivity. So in practice, we usually use a variable FQT, and then this variable is not observable by the firms. So then over time, employees will rely more on these hard to observe correlates of productivity, and then rely less on group average productivity. So as a result, the model predicts that wage coefficients on FQT will rise with experience, whereas coefficients on group dummies should decrease. So using this idea, Tonjan and Piret, so they basically test this model, and then their main finding is that there's strong evidence on employee learning, but there's little evidence for race-based statistical discrimination. But one key assumption of this literature is that employee learning is symmetric. That is, the current employer and outside employers, they have the same information about workers' productivity over time. So natural question is, what if employee learning is asymmetric? So in reality, we can very intuitively, think outside employees may have less information than the current employees, because current employees have like day-to-day interaction with their workers. So this is sort of where this paper, the motivation for this paper comes in. So we have this literature on employee learning pioneered by Farber and Gibbons, then later on, applied to try to test for statistical discrimination, but still under the assumption that learning is symmetric. And then there's another sort of separate line of research which try to test implications of asymmetric employee learning models. And then what this paper tries to do is sort of combine these two literature and try to test for statistical discrimination when we allow employee learning to be asymmetric. And if the learning is asymmetric, then the tenure and experience will have different impact. So the idea is that if learning is symmetric, then the learning is continuous, even with job turnovers. So therefore, learning will take place over general labor experience. Whereas if learning is asymmetric, then learning will take place over tenure, and whenever workers change jobs, some of the information will be lost. So in the extreme case, if all the information will be lost, then the learning will only take place over job tenure. And these differences will also generate implications for racial discrimination. And we're going to test for these implications using the NLSY 79 data. And what we find is that, so we find strong evidence for asymmetric learning and statistical discrimination against Blacks among non-college graduates, basically in the unskilled labor market. On the other hand, we also find that employers can directly observe most of the productivity for college graduates at hiring, and they learn very little over time about these workers, these more high-skilled workers. So I'm going to first discuss a very simple.
So there's a question, two questions from Peter.
Yes, please.
In this literature, first of all, how do you deal with the possibility that there are long-term contracts? And then secondly, what I wonder, if you stick somebody into a dead-end job, how would you learn about what they could do if they were in a better position? That seems like a bit of a problem for this learning literature, right?
Yeah, so I will talk a little bit about, so for your second question, I have some more direct response. So we're going to do some think about this as an alternative hypothesis and testing the data. And then in terms of your first question, thinking about the long-term contract. So, we have not, specifically account for that right now. Okay, this is sort of the short answer, but I'll come back to your second comment when we come to the empirical work. So thanks for the question. So we're gonna think about a very simple signal extraction problem. So just to motivate the empirical test we're gonna do on the asymmetric learning and statistical discrimination. So I don't mean to, so this is not a theory paper. So the theory is really just to motivate some of the empirical tests we're gonna do. So the workers have some productivity Q. It's a random draw from a normal distribution with a mean mu and some variance. And then employees do not have complete information about the true productivity. So then they draw some signals. Okay? And then the first period, they have a signal we call S1, and then with a mean, the true productivity and some noise, epsilon. And this noise is normally distributed, so a very standard assumption. And then the expected productivity after first signal is gonna be a weighted average of the group mean, mu, and the signal, S1. And then the weights, theta, so this parameter, we call it learning parameter. So it's gonna be just a ratio of the variances. And when the signal is perfectly informative, so the sigma epsilon equal to 0, then theta 1 will equal to 1. So the population mean is completely ignored. So you have the complete informative signal. And then, but if the signal is pure noise, sigma epsilon equals infinity, then theta 1 equals 0, then the only information essentially the employees have is a group average. So they'll use a group average to predict the expected productivity for the worker. And then now suppose we consider multiple signals. So over time, the employees will receive more signals. And then they expect productivity again, so they just use the Bayes rule and then update their belief. So it's going to be remain a weighted average of the population average mean, and just a summation of all the signals. Okay, so again, so the weight is determined by this learning parameter theta t. So as we can see from this formula, the learning will increase over time. As t goes to infinity, the theta t will go to 1. So meaning at the beginning, so the firm, since they don't have much information, so they rely a lot on the group average. But then over time, so as they learn more and more, so the workers' expected productivity gets closer to the true productivity because the signal becomes more and more accurate. And so what's the implication of this employee learning process? Okay. So now suppose a researcher observe a wage and also the one-time signal productivity. And this one-time signal is not observed by the employer. And then so in the empirical literature, so the signal is usually measured by this FQT score. And then we can derive the covariance of the signal or FQT with expected productivity, which is a wage, as following, so which is just theta t times the variance of Q. As we already showed, the theta t, the learning parameter, increases in t. So immediately, so that's a main implication of the employee learning. So the wage will become more and more, covariate, with FQT over time because of the learning. And then now we consider a case when there are multiple jobs. So consider worker hired by a new employer in period T. So now, we have to consider two, patterns of learning. So if learning is symmetric, then the employer has the same information about the worker's productivity. So the new employer will have the same information as the current employer. So therefore, the theta t will evolve just as if the worker stays with the same employer as before. Whereas if learning is asymmetric, then the new employer will have less information than the current employer. So the theta t will become smaller. So if the new employer does not learn anything from the work history, then the learning parameter actually will be reset to the first learning parameter theta 1 when the worker changes to the new job. So this is the second implication of this model or this framework. So if learning is asymmetric, then the learning will take place over tenure. Whereas if learning is symmetric, then employee learning takes place over general labor market experience. What about statistical discrimination? So now we introduce some covariates. So X, say, education will be such a covariate. So which is correlated with this mean of the group, and then race. So if used by the employer, so that will affect the anti-conditional mean mu. So in this formula, so in this prediction for the expected productivity. And then, so statistical discrimination here will mean that, the mu conditional of X, the blacks, the perceived average productivity is lower than the whites perceived average productivity, even conditional on other characteristics. So here we're agnostic about why statistical discrimination happens. Obviously it's illegal. So maybe because the employees so they have some sort of perception, whatever. So we try not to this is not a model try to understand why this statistical discrimination generates. Okay? As time passes, the employees will rely more and more on signal series. So as we showed earlier, and less on these other variables, including race.
Can I interrupt? So how
Sure.
do you distinguish asymmetric learner from something like firm-specific human capital? Wouldn't that also reset things?
So the firm-specific human capital, so we'll capture using the pure tenure effect. So this, so we're really just looking at the learning, through these job transitions. So the learning parameters, and so as a result, the implication of the model is that if the blacks are statistically discriminated against, then the coefficient on black dummy will be negative, but its interaction with time is positive because of learning. So So Black will be discriminated, but then they discriminate less because they review their true productivity over time. So these are the main implications of this simple framework. So if we bring this implications into a very simple regression models, so we'll have some regression equation like log of weight and very standard, and then individual FQT and FQT interact with time, because we want to distinguish this learning symmetric versus asymmetric learning. So we're going to look at two different measures for time: general experience versus tenure, and then also Black and Black time interaction. Okay. So if this alpha coefficient, so the coefficient of FQT is positive, so that means employers will have some initial information about the true productivity of the worker. And then if this beta, so FQT time interaction coefficient is positive, that means they'll learn over time, so which covariates with FQT more and more over time. And with asymmetric learning, so the learning will take place over tenure. Then if we use the tenure as a time measure, so the beta coefficient will be larger if we use experience as the time measure, the coefficient on the interaction term. Because under asymmetric learning takes place over tenure. So the learning is faster over tenure. Whereas if learning is symmetric, so everything is opposite. So the learning will take place over experience. And so therefore the beta coefficient on experience interaction will be greater than the beta coefficient on the tenure interaction. So similarly, the model also has implications on statistical discrimination. So if gamma, so which is the coefficient on Black dummy, is negative, so that means employers statistically discriminate against Blacks at the time of hiring. And then if delta is positive, that means they discriminate less as they learn over time. So again, with asymmetric learning, and statistical discrimination, so the learning takes place over tenure, so the tenure interaction terms coefficient is larger than the experience interaction term. Whereas if there's symmetric learning, then the experience interaction terms coefficient is greater than the tenure interaction terms coefficient. So next, we're just gonna bring these implications to the data. So the data we use is a 2008 release of the National Longitudinal Survey of 1969. And we restrict the sample to Black and white male workers with at least 8 years of education. So just following the literature. And we construct individual monthly employment status using NSY, work history data, and then follow workers over time since they first leave school. And we standardize FQT scores to have a 0 mean, standard deviation 1 for each 3 months age cohort. And at the end, our sample consists of about 2,600 whites, 1,100 Blacks with about 320,000 person month observations. So we divide the sample into two education samples, one a college with at least 16 years of schooling, and then a non-college sample with less than 16 years of schooling. And so these are the descriptive statistics. So as we can see immediately, so on average, so Blacks have, the average FQT score is 1 standard deviation lower than that of whites, even conditional education. So this might be, the source of the statistical discrimination. So the employers may use this information to interpret, to perceive the average, productivity difference between the Blacks and the whites. And then on top of this, FQT difference, we also see that Blacks on average are less educated. So they also have, on average lower tenure and experience, which are not shown here, and then lower wages. So our benchmark specification essentially is just the regression model I showed you earlier. So we use 2 time measure, experience and tenure in months. So in our regressions, all the months values are divided by 120. So therefore, all these coefficients on the interaction term with time interaction term can be interpreted as like changes within 10-year time period. And so besides FQT time interaction, Black and Black time interaction, we also control for a bunch of other characteristics, like say education and education interact with time, and then region, year dummy, and then importantly, we also control for a time experience profile, the polynomial experience profile, to account for any human capital, changes over time, besides, employee learning. So the main interest, main coefficient of interest are the coefficient on FQT and black, and then also the coefficients on experience tenure interactions with FQT and black. So before we move on to show you our results, so let me first show you our data actually can replicate well the Altonji and Perret results, the 2001 QJE paper. So the first column in this table is directly taken from Altonji and Perret's paper and their main result. So they essentially use a 1992 wave of the NLSY 79, and they find that so the FQT experience interaction term is large and significant, and they interpret this as learning, evidence for learning. And then they also find that once you have the black experience interaction, so the black initial coefficient, even though it's negative, it's small and insignificant. So they interpret this as there's little evidence for race-based statistical discrimination. So when we use our data, so remember our data is monthly, so we essentially replicate their result. We find that there's strong evidence for learning, but then there's no evidence for this initial black coefficient to be negative and significant. So there's little evidence for race-based statistical discrimination if you use this specification. And then on the third column, so we use our full sample, since our sample is to 2008, so we essentially get the same, interpretation, same result. So there's learning, but there's no statistical discrimination.
So Sue, can I ask a question? So
Sure.
For the interpretation, so AFQT interacting with experience, both in Altonji and Perret were interpreted as evidence for learning, right?
Yes.
So, but experience, the recent macro literature actually have found that, for example, the return to experience vary a lot between developed economies versus less developed economies. Higher, return to experience is higher in more in the US, for example, than in China.
Yes.
And that led some, one possible explanation for that is return to experience. A lot of it is coming from cognitive, is related to whether the task is cognitive or non-cognitive. Now, AFQT obviously is a measure of cognitive skills, right? So could this be that AFQT interacting with experience, that coefficient reflecting the kind of tasks that the individuals are doing, right? So cognitive, if this could be just an evidence of return to experience is higher in cognitive skills,
so
cognitive tasks.
So that's a great point. So first of all, I think my understanding is that at least between the U.S. and China, so the return to experience, the large difference is because the labor market institutions are quite different. So
I use the U.S. versus China example, but actually the paper in JPE, like Goka said at all, they were not including China. They were comparing U.S. with other economies, but the pattern is applied to China.
So I think it's certainly it's certainly possible. So this is like it's certainly possible, and there's so these days we have a lot of new data. We can actually look at occupation and occupation transition. So what we have done here is at least initial occupation doesn't matter. So we haven't done what we haven't done is follow the individual and look at occupation transition over time. And then of course, the way we, at least, most of us, available data for us is, to use a detailed occupation to, to classify different skills and so on. So that, we don't know, it's certainly a possibility, but I can tell you is at least the initial occupation sorting and then the skill requirements of the initial occupation, even conditional on that, all these effects still holds. Okay, but that's a great question. So I agree with you, that's certainly a possibility. And so basically, so from what we learn from this, existing literature is that, FQT becomes increasingly more important in explaining wage over time. So this is interpreted as learning. And then there's no evidence for statistical discrimination on race, conditional upon being hired in the first place. So of course, discrimination could take the other form that, some people just never got hired because we are looking at wages. So already this is a conditional hiring. And then employers on average do not use race to infer productivity at time of hire. Given that, if we assume that employer learning is symmetric. So this exists in literature, so they assume learning is symmetric, and then the other assumption they assume is that productivity is equally unobservable or observable for all potential employees. But there's evidence that college graduation actually plays a role in signaling or revealing ability to the labor market. So a paper by C.T. Akano and his co-authors show that, so the information is contained in CVs, such as grades in college, majors you study, extracurricular activities, and the college you attended actually reveals a lot of information about individual's productivity. So therefore, we're going to test the employer learning statistical discrimination model for non-college graduates and college graduates individually. So first, let me show you the results for the non-college sample. So the first column, so I present the coefficients of the main coefficient of interest when we use actual experience as a time measure. And then the second column, we use tenure as a time measure. Okay? So first thing we find is that, so the initial FQT coefficient are significant, positive, and also very similar between these two columns if you use experience or tenure as time measure. Basically, some information is reviewed, or employers have some information about this workers' productivity, but it doesn't matter if you're the initial employer or the subsequent employer. So they essentially learn the same amount of information, similar amount of information. Okay, so which is consistent with asymmetric employee learning. And then the second coefficient of interest is to look at this FQT experience interaction term and FQT tenure interaction term. So there is certainly learning over time, but then there's also strong evidence that the learning takes primarily over tenure. So the speed of learning is much faster over tenure than over general experience. So therefore, confirming our hypothesis that learning is asymmetric over time. So if learning is asymmetric over time, then we should really focus on our second column to look at the rest of the result. So what we also find is that Black workers at time of hiring, so their wage actually is 12.7% lower than equivalent white workers. Okay? And then also there's some evidence that the Black tenure interaction term is positive, so there's some learning over time, although the coefficient is not statistically significant. So therefore, we find that we find strong evidence for learning, and then evidence on asymmetric learning, and then also given learning is asymmetric, we also find strong evidence for statistical discrimination against the non-college graduates. Okay?
There's a question from Scott that why don't you run regression with both?
Oh yes, that's a good question. I'm gonna run regression for both. Okay, so but I will show you in a minute. Okay? I promise. So then the results for college graduates actually is very different. Okay, so for the college graduates, so the initial FQT have very large statistical significant coefficient, meaning essentially most of the productivity is reviewed or signaled to the potential employers. And then therefore there's very little scope for learning over time. So FQT experience interaction, FQT tenure interaction, both are very small and statistically insignificant. Okay? And then in terms of the coefficient on Blacks, so for the college graduates, actually we find that the initial coefficient on Black are positive, large, and statistically significant. So as a matter of fact, we are not the only one who find this wage premium for high-skilled Black workers. Some other people have found this. And then one interpretation for this is, so again, remember these are conditional FQT. So maybe there'll be some sort of selection effects. Some people argue that the tests like FQT are racially biased. So for Black and white, taste, students, so conditional FQT, so Black students actually have to be better. So that might be, reflecting, this premium might be reflecting this, innate ability difference. So another explanation is, some papers like, the economic check-up paper by RCD Diacono, so they argue that, say policies such as FQT, affirmative action, I'm sorry, so affirmative action, so they, under those policies, so employs value diversity. So they may have an incentive to recruit, highly skilled, Black workers in certain positions. So because the supply is very small, so this, this demand effect may drive up the Black wage premium for the high skilled workers. But what's also interesting is that, so the Black,
you have 2 minutes.
Oh, okay, Black's experience and Black tenure coefficients are, negative. So even though there's no evidence for statistical discrimination, so there might be some other, form of, discrimination going on because, lack of promotion or training and so on. Okay. So I'm gonna just skip this. So, we find, evidence for statistical discrimination for non-college graduates, but then no evidence for college graduates. Okay. And then, so let me just go directly to that question to respond to that question. So essentially, earlier we're just saying we're testing for like a symmetric learning versus purely asymmetric learning, basically assuming that outside firm have no information about the workers. What if an outside firm have some information? So then learning will take place over both tenure and experience. So this is our second column. So the first column we just just taken from the results with tenure for the non-college graduates because only matters for non-college graduates, the learning. And then what we find is that once we put both tenure and experience in there, so learning indeed takes place over tenure. So there's very little learning takes place over general experience. Okay. So, and even if we include both tenure and experience, so we have, we still find strong evidence for statistical discrimination. The initial Black coefficient is negative, and then some evidence for learning over tenure. And then the second robustness is sort of responding to Peter and Hamin's earlier question. So what if it's all sorting? So Black and whites, they're sorting to different occupations, different sectors, different industries with different skill requirements. Okay, so we find that even after we control for initial occupation or initial industry or both, so all these results stay the same. So we still find learning takes place over tenure, and then we still find strong evidence for statistical discrimination for the low skill Black workers. Okay. Maybe I just use very quickly 1 minute to talk about some implication on job mobility. So if learning is asymmetric, then whenever changing employers, the high skill workers and low skill workers will be pulled together because the new employers have no information about the true productivity. So therefore the high skill workers will have less incentive to move. On the other hand, if say the minority workers, Black and non-college workers, they are discriminated each time they move because of asymmetric learning, so they will also have less incentive to move. So this is the implication of the model. So if we bring this to the data, so indeed we find that the Black non-college workers, so they are less likely to move, conditional FQT. And then also high skill workers are less likely to move. Okay. And then for college graduates, since there's no discrimination, statistical discrimination, and so therefore we do not find any significant effect of Black on job mobility. And to summarize, so we find strong evidence of asymmetric learning for non-Black, non-college Black workers, and also evidence for statistical discrimination, but then there's no evidence of Black college graduates being statistically discriminated. Okay. Perhaps they have better information about their productivity. So the policy question is, how to sort of rectify information asymmetry in the unskilled labor market, right? So it seems like, for the skilled labor market for the college graduates, so the CVs have a lot of information. So can we create something, similar for the unskilled workers? And then we also find in some preliminary analysis that, if the Black workers, working for older employers or a Black, supervisors or smaller firms, so they seem to be, less discriminated, at least in terms of statistical discrimination. So is this the information we can, help to, design policy, in the near future? And then finally, so, there's still, remaining, challenge, in this line of work. So we construct a simple signal extracting model to illustrate the effect of asymmetric learning and statistical discriminations and empirical implications. But we're still trying to work on an equilibrium model of asymmetric learning and statistical discrimination. So some of the issues I think Peter also talked about in his paper. So how to, when learning is symmetric, how to model wages endogenously, and then in terms of dynamics, how to model the job transitions. So these are not straightforward questions. So these are something we're still working on. So if you guys, if anyone have any comments or ideas, please let me know. Thank you.
So can I ask a question?
Yes.
So I guess it's related to the last item on your concluding slide. In the end, toward the end, you talk about the implications of different type of learning for Black and white regarding job mobility.
Yes.
But then, to the extent that workers of different ability, like AFQT measure, react to these, the discrimination or learning differently in terms of job mobility, it should feed back to the inference problem that you initially worked on, right? So
yes.
Okay, so that's, I think, probably what you are already on your mind.
Yes.
The other question is, I think, related to what Peter wrote in the chat box. What if initially, I mean, you're assuming the signals that employees are observing just emerges automatically, regardless of what tasks that the worker is assigned to. Some important distinctions about tasks are, some tasks may be generating useful signals about the worker's ability. And then some tasks are really dead end tasks. There's nothing useful for the firm to learn about the worker's ability. I don't know if there are detailed job assignment information that you can use, but it will be, or without that, I don't know if you can do something about some kind of discrimination in the form of task assignment, where the tasks differ in the frequency of useful signals, emerging on the job that the workers are assigned to.
So this is a great comment again. So your point is well taken. So I think so we don't have information on exactly the task each worker is assigned to, but we have information on occupation. So that's the inference we can make. So look at the job mobility, and then look at the occupation transition, and then also look at the skill requirement using ONET, DOT, and then to look at skill requirements, and then to look at basically essentially given the different skill requirements, to try to figure out whether there's some differences in signaling revealing or signaling extracting condition on these these skill requirements on particular occupation. So that's certainly a direction we can further explore. Thank you.
Okay, thank you. So then now we have 10 minutes coffee break, and our next talk will start at 3:30.
That's awesome. Finally, a real coffee break.
Hi, Peter. So can I ask you something?
Yes, absolutely. You can ask me something. Yes.
Yeah. So because you talked about like this endogenous wage in your model. So I'm curious, what's your plan to endogenize your wages in the model?
Well, so
please don't. I mean, if you do that, it's going to give me a big trouble. So
I know it's very difficult because we have the same challenge. So that's why I wanted to ask you earlier, but Red asked the same question.
So the first step we've been thinking about isn't exactly endogenizing it, but just having something idiosyncratic in the matching, so that instead of just having one wage at the in each sector, have sort of a wage distribution in each sector. The reason why we think that could actually be useful is that we would get some sort of, we would get reservation wages as opposed to just these accept, reject decisions.
Mm-hmm.
And in terms of how actually we've been thinking of trying something adverse selectionish in terms of the wages, but I guess Teddy, he may be a bit more pessimistic than I am, but I think it could get.
So, I mean, so we actually thought about, we have the same issue in our paper, which I'm going to present. We thought about things, and the problem is that, there's a private information. So now, thinking about the, the right, the trading mechanism is not a trivial question. It is actually a very hard question.
Yeah. So we have.
Right. So you can create signaling, and but what about if you don't do signaling? Then are you going to think about doing this like screening mechanism? That's also could be too complicated. And also, like there are things you can do, but they actually create their own problems. So instead of really helping us think about the issues we are studying in the papers, they actually create other issues.
I have some comments on you. You're saying.
Oh, sorry.
just following up on what you're saying, it is hard. I mean, if you did bargaining, so in job search, there's two main approaches: posting and bargaining. Bargaining with private information is kind of complicated, as you well know. Posting, you could end up with a separating equilibrium if you did, posting with directed search. I'm not sure that might work well for you. Those things can be fairly tractable. The question is, would it still lead to discrimination? Well, let me say this is a first order issue. This is not a detail. One view against the discrimination view is, look, if we were really paying type A workers less, well, they'd be bid away by other firms. So it couldn't be, the wage would be bid up. So you really have to get wages in the model, I think, to have a complete analysis of discrimination.
But Randy, I think also like I agree with you. I mean, of course, we are economists. We want to think about prices. Where the, right? So, but also like there are like markets where you actually don't have control over prices. Like the prices can be actually set by the let's say like the platform. Like what about Uber? Right, so you don't negotiate with the driver, so prices are actually set by the platform, and I don't think they actually like set different prices for like different like people. Okay, so I mean I agree with you. I mean the thing is that we want to think about it, but also this is the thing so what is our final goal? Is it going to be about we want to identify the trading mechanism that allows to get rid of the discrimination, or is it going to be that so with exact prices we have a certain result where is it going to be enough for us to just see whether the results are going to survive even if we do something else, or you know what I mean, right? The space of or trading mechanisms is just so huge. So I don't think there's it's possible for us to really cover all possibilities. So I mean,
I still agree with Randy that it would be nice to have the wages being endogenous in these sort of models, and I think it's worth a try.
But I guess Peter, you are the expert. That so not in the kind of models we study. Like what about in in old days? I believe that you actually have a paper that endogenize prices in the wages in Cote and Lowry.
Yes, no, that is true, and that is not so bad because the model is static.
And the things don't really change much.
So the Cote and Lowry model gets much more interesting with endogenous wages, sort of, and that's kind of consistent with what Randy is arguing here. So, I mean, I just think.
So are you saying that even with endogenous prices, you could actually show that the result in not all the result, maybe important result in Cote and Lowry actually survive? Is that what you're?
Yeah. Yes.
Yes. So that is true, but then the endogenizing wages allows you to do other things as well, because then you can tie wages to some underlying production technology, which is sort of, I guess, Randy's point here. And by doing that, you get a richer model where you can get complementarities. And unlike if you think about black-white discrimination, the Cohen-Laurie model is not a model about conflict, but the model that endogenized the wages now turns into a model where there is conflict between groups, which I find interesting.
Or if the production is
Yeah.
aggregate production function rather than linear separable
Right.
production line.
Right. Well, I mean, it could come from preferences. You could have linear technology, but just convex preferences for different goods. That's going to do the same thing.
But Peter, in your setting, you are saying in the search, in the random matching setting, if wages were bargained or posted, you have tried this?
Yes. I mean, it's not that we totally failed. I just, we haven't completely been able to nail the equilibrium yet. But I mean, the most straightforward way to sort of
This is like a pen reunion. Do you notice that?
Hey, Randy.
Hi. like the glory days at UPenn.
Oh, good.
So Peter, but so what did you try? Like what kind of pricing mechanism did you?
Well,
try?
the most obvious one is to do some sort of surplus sharing, right?
I know, but like I think I learned this from Randy that you don't want to do niche bargaining with incomplete information. So like you should just never do that. I don't know whether it was Campbell that or it's Randy, but one of them said that don't do niche bargaining when there's a private information.
Right.
Well, so the alternative then is to do some posting, and I've tried that much less, but it also seems, for the reasons you are mentioning, the signaling kind of issues, that it's not obvious how to do that.
Well, you might set it up as a screening model, not a signaling model, which kind of makes sense. The employer is posing the wage. The workers are the ones with the private information.
So
right?
Randy, you want us to do the Gary Scheinman, right?
Well, it's something that works. I don't know if you want to do that, but I mean, it's an example that works in the sense that you can handle private information. And it doesn't give efficiency. It tends to give uniqueness, but I don't know. It's something to try. You can do bargaining with private information, but you probably shouldn't do some axiomatic bargaining.
Yeah, I guess, I mean, the simplest non-axiomatic would just be to have one side make the offer with some probability, the other side making the offer with some probability, right?
Yeah, maybe.
No, the signaling, right?
But maybe we could deal with the signaling, right?
Okay, everybody, thank you very much for
Great
awesome conversation
John.
during the coffee break, but it is 12:20 where I am and maybe 2:20 where you are. And now it's Ariada's turn to tell us about her paper. Go for it, Ariada. You're still mute right now, though.
Trying to find the unmute button. Can you see my screen?
Your screen is frozen.
It looks
Okay,
very
so
interesting. But we hear you.
That's, I guess, good news. So let me try that again. I believe you can see my screen now.
Yes, we can.
Perfect. So thank you very much to the organizers for including the paper in the program. This is a joint work with Yinyi and Bruno, who are both at Northwestern. And Yinyi will be answering questions in the Q&A. So this paper incorporates dynamics into the basic
Ariana,
model of...
sorry to interrupt.
Yes.
So it seems once you go to the full screen, we cannot see it's right now it's black. We cannot see your full screen.
So that's good to know. Let me try that again. I'll try that one more time. And then if it doesn't work, I'll just work with a smaller. So let's try that again. Can you see the
No, the full screen doesn't seem to work.
Okay, so I'll just, unfortunately, I think I'll have to keep the smaller screen. Okay. Can you see it now?
Yes.
Okay,
yeah, this looks like full screen.
Actually, it works now. Yes, so useful trick for the future. So this paper takes, as I said, the dynamic perspective on statistical discrimination. We're starting from the observation that upon entering the labor market, workers have little to show for their productivity to their potential employers. So employers are facing scarce information about potential workers when they're making their hiring decisions. And therefore, they're tempted to use easily observable characteristics, such as race or gender, to base their hiring decisions on. Despite such practice being illegal by anti-discrimination laws, we have quite a bit of evidence that shows that empirically, at least, employers are using, are making such inferences based on group membership at the hiring stage. Of course, once workers are hired, they get to perform on the job, so they get to generate more information. So employers will eventually learn about the true productivity of workers, but that might take time. And especially in settings in which jobs are scarce, groups that are favored at the beginning might get a huge advantage from being the first to be hired. On the other hand, groups that are discriminated might miss on those early opportunities, and that might impact their lifetime payoffs in important ways. And notice that under such job scarcity, this could happen even when the groups are quite comparable in their productivity distributions. So the questions that arise naturally in this setting is, first, how important is such early career discrimination for workers' lifetime prospects? And secondly, as the distributions, the productivity distributions of different groups converge, should we observe that their payoffs converge as well? And here I'm referring to lifetime payoffs, lifetime earnings. There are two conjectures that that could potentially address the second question. So on the one hand, we could naturally think that if we start with a small difference in productivity, the worker who is hired first, so the group that is initially favored, will get that first chance. But employers will learn about the true productivity of the worker. And therefore, errors in the hiring decision that was made at the beginning will be revealed pretty quickly and will be corrected rather quickly as well. So this implies that small difference at the beginning should have no large difference in the worker's lifetime earnings. So we should see little impact of group belonging. Another perhaps equally plausible conjecture is one that suggests that small difference could actually spiral into very large lifetime differences, lifetime payoff differences. The favored group, the group that is hired at the beginning, gets access to early career opportunities. And when these early career opportunities are very important for the career path of a worker, we should see that very small differences at the beginnings will spiral into rather different career paths for workers of different groups, and that will snowball into a large impact of group belonging. So the key insight that we'll put forward is that how employers learn about workers' productivity over time matters a lot for which of these conjectures is right. So we'll be able to say that the first conjecture is actually the one that, that gets realized in certain learning environments. In other learning environments, the second conjecture will take place. And in fact, we'll be able to provide a systematic classification of learning environments based on these two conjectures. So I'll start with the simplest model possible in order to communicate the insight sort of in a very clean way. And then we'll see that that insight actually is quite robust as we move to a richer dynamic matching model. So there will be one employer and two workers, A and B. Each worker comes from a distinct social group, so we have groups A and B as well. The productivity type of worker I is binary. It's either high or low. We'll use theta I to denote the productivity type of worker I. We'll assume that so first we'll denote the average productivity of group A by PA and that of group B by PB. So this is the probability that a worker from that group is a high type. And one of the major assumptions that we'll make is that, or rather the approach that we take here is that we look at comparable social groups. And by that, I mean that even though we'll say that group A has higher productivity than group B, so PA is strictly greater than PB, we want to look at the case, at the limit case in which groups have almost identical productivity distributions. So we'll have a particular focus in very small differences, ex-ante differences. So we'll look at the limit of as PB goes to PA. This model will be set in continuous time. All three players that we have so far will be long-lived. At each time t, the employer will allocate a divisible task between to either worker A, worker B, or he will dispose of the task and take an outside option, and we'll label that as a safe arm. So the employer's problem here is a standard three-armed bandit problem, where this third option, this outside option, is a safe arm that gives a fixed payoff, a fixed and known payoff. The flow payoffs of the employer are rather simple. If the task goes to a high type worker, he'll obtain flow payoff V. If it goes to a low type worker, the employer obtains 0. Otherwise, if the task is disposed, so if the employer chooses the safe arm, the flow payoff will be something between 0 and B. We'll denote that by S. The worker's flow payoff, on the other hand, is for the moment a fixed wage. We'll normalize that wage to 1. Hopefully towards the end of the talk, I'll be able to talk about flexible wages and how we're thinking about them as well. But in this baseline model, I'll keep things rather simple. So if the task is allocated to the worker, he gets a unit flow payoff. Otherwise, he gets 0. That's his outside option. Crucially, we're saying that the employer learns by allocating tasks. So the employer learns about type theta I, if and only if the task is allocated to worker I. As I've sort of previewed at the beginning, we'll be contrasting two classes of learning environments. And right now I'll start with the two very stark learning environments, breakthrough and breakdown. In the breakthrough learning environment, the high type is generating a signal with some probability and generating no signal with complementary probability. The low type generates no signal. So if you see a signal as an employer, you know for sure that that signal is coming from a high type. So you should think of this as a sort of a scientific discovery that a researcher has done that proves conclusively, for instance, that he's a high productivity type. So we'll refer to this signal as breakthrough from now on. In the alternative learning environment, the opposite is the case. So the low type generates a signal with some probability, and no signal otherwise, the high type always generates no signal. So if a signal is observed, that is for sure coming from a low type. So it perfectly reveals a low productivity type. So we'll refer to this as a breakdown. So these are the sort of the very stark learning environments that we're comparing in this talk. How do signals arrive? Well, we'll model signals as Poisson signals, and they arrive at rate lambda h and lambda. So lambda h for the breakthrough environment and lambda l for the breakdown environment. So the model is done. It's a very simple model, but let me take a minute to interpret these two learning environments that we've just put forth. We're thinking of the learning environment as an intrinsic feature of the job. So it varies by occupation, it varies perhaps by rank within the organization, and so on. And essentially, it's a way in which the employer monitors the worker. In the breakthrough environment, the employer is essentially monitoring overperformance relative to some notion of standard performance. In the breakdown environment, the employer is monitoring underperformance relative to a standard notion, to a notion of standard performance. And here, when I say to a notion of standard performance, I'm really referring to the no signal in the model. This classification, so breakthrough and breakdown environments, capture pretty well job typology that was conceptualized first by Jacobs, and later it was informally elaborated by Baron and Krebs. So in this job typology, there are two types of jobs, star jobs and guardian jobs. Star jobs are very much like our breakthrough environment jobs. Guardian jobs are very much like breakdowns. So let me quote Jacobs to give you a sense of what do I mean by star jobs. So he says, the first-rate salesman can often add a significant increment to the performance of his organization, while a less productive or his inferior will not impose unacceptable costs. So these types of jobs are jobs in which it really matters whether the worker can generate that breakthrough, that success, whereas standard performance does not hurt the organization or the employer as much. You perhaps want to think of these types of jobs as R&D, basic research, perhaps academic research, high stakes sales, and so on. Guardian jobs, on the other hand, are more like our breakdown environment. These are environments in which mistakes or failures matter a lot. So Jacob says, the airline pilot who misses a landing or the operative who inadvertently blocks a long assembly line will produce rather destructive effects. But if they do a perfect job, then that goes pretty unnoticed most of the time. So these types of environments are environments in which it's failures or breakdowns, those that matter, and those that are tracked by the employer. So just to sort of summarize the model that we've seen so far, what are we asking from this model? Well, two questions. First, we'd like to understand, do workers' lifetime payoffs converge as PB goes to PA? So as the productivity distributions of the two groups are converging, do the chances that these workers get in the labor market matter? And secondly, which learning environment, if I know these two, is the one that is granting a disproportionate first hire advantage? Okay, so let me see in terms of time. I think I want to skip the discussion of the literature so far. Let me just point out that the approach that we're taking in looking at the limit case between as PB goes to PA is really inhabiting that space between Phelps and Arrow's models. So it's true that just like in Phelps, we're looking at prior productivity differences between groups, but we're really trying to sort of make those productivity differences very small, therefore potentially converging to Arrow's model. Okay, so let's start with analyzing these two learning environments. Let's start with breakthrough learning. The first observation that we need to make is that at each time t, the employer allocates the task to either the worker that is more likely to be a high productivity type or to the safe arm. And the safe arm here corresponds to a belief threshold P underbar. This will really be the case in both learning environments. So we'll see that in breakdown as well. So at time 0, PA is above PB. So group A starts as more as ex ante favor. We'll assume that both groups are preferred to the same arm to start with. And by the way, here I have time in the x-axis and I have employer's belief on the y-axis, and I'll use red to denote instances in which worker A is the one that's being hired. So because PA is greater than PB, worker A will be hired first. He'll be allocated the first task. Remember that in breakthrough learning, it's either no breakthrough or breakthrough. As long as no breakthrough is observed, the employer is becoming more and more pessimistic about the worker's type. Therefore, his belief is going down. If a breakthrough is generated, his belief jumps to 1, and the employer hires or allocates tasks only to worker A from that point on. But if no breakthrough is realized, the belief will continue dropping down until it reaches PB. So this, at this moment, when the belief about worker A becomes exactly PB, the employer is indifferent between the two workers. They look on average exactly the same. So from T star and on, the employer will alternate between the two workers. So he'll mix between the two workers. Think of this as essentially the workers taking turns to perform the task. And because he is mixing equally between the two workers, the belief for each worker will go down in the same way, in the absence of a breakthrough, of course. But if a breakthrough is realized, say if worker B realizes a breakthrough, his belief jumps to 1, and from that point on, it's only worker B who is being allocated tasks.
Can I ask a clarifying question?
Please.
By mixing, you mean splitting between the two of them? Or I mean, alternating may be a little bit confusing here. Alternating sounds like, you know, going between the two in some order. You mean actually the splitting it exactly at each point, no?
Yes, I mean exactly that. So you could think of this as essentially randomizing over time, right? So randomizing over very small amounts of time between each workers, or flipping a coin at any point. Does that answer?
Yeah, so in the discrete approximation, you'll be actually alternating.
That's right.
In the continuum, it's like arbitrarily, you know, small interval in some sense. Right? Yeah.
Absolutely. So in a sense, the colors I'm using here, you know, it's only for illustrative purposes that you can see like a region of blue. It should really be purple. So
yeah, exactly.
In the sense
That's
that
what I was
mixing between the two colors.
Yeah.
Good point. Yes, thank you. In the absence of a breakthrough, the belief is going down, and as you can probably predict by now, it will hit P underbar at some point. In which case the employer, or from that point on, the employer will switch to the safe arm. So this is the dynamics. Our result here is that as PB is going to PA, the expected payoff of worker B is converging to that of worker A. So now let's try to think about the intuition that we just got from the graph. There was a first phase during which the employer is only allocating the task to worker A. And subsequently, the two workers were, so from T star and on, the two workers were treated symmetrically. The amount of time that worker A is getting so that he performs the task by himself, just him, is proportional to the difference between PA and PB. So that's to say, so this expression here gives us exactly the duration of that first phase during which only worker A is being favored. As PB is going to PA, this T star is shrinking to 0. The grace period that worker A is obtaining is shrinking to 0, And with that, the first higher advantage of worker A is vanishing. This is the intuition for why, as the productivity distributions of the two workers converge, the expected payoffs of the workers converge as well. Now let's turn to the breakdown learning case. Again, the optimal allocation rule is such that the employer either hires the most productive of the two workers or the safe arm if they're not looking as if his belief is not sufficiently high for either. So same picture, worker A will be hired first, but in sharp contrast to what we just saw with in breakthrough learning, here, in the absence of a breakdown, the belief that the employer holds about the worker goes up. So for as long as the employer is not observing a breakdown, he becomes more optimistic that the worker is a high type. And that means that once he hires worker A and the worker A does not generate a breakdown, that's good news. The employer wants to continue hiring worker A. And that is the case until worker A generates a breakdown, potentially if he's a low type, at which point the belief of the employer will drop down to 0. And from that point on, the employer will try worker B. Same dynamics. Worker B will be generated until he generates a break. Worker B will be hired until he generates a breakdown. And if he generates a breakdown, the employer will switch to the safe arm. Now let's try to run through the same exercise here as well. So what happens in the limit as PB goes to PA? Our second observation is that as PB goes to PA, the ratio of the expected payoff of worker B to that of worker A is in the limit strictly less than 1. So that's to say, in the limit, arbitrarily similar workers are getting very different payoffs. The limiting payoff of worker B is strictly below that of worker A. So let's think about the intuition that we got from this graph here. So worker A is again being favored at the beginning. If he generates a breakdown, then we're switching to worker B. The crucial observation here is that the time that worker A is getting does not depend on how far PB is from PA. So let me quickly go through the payoff. So if worker A is a high type, he never generates a breakdown, he gets a payoff of 1. He is hired for a lifetime. If he's a low type, he will generate a breakdown eventually, but there is some expected time until a breakdown, and he enjoys the benefit of being hired until then. Worker B, on the other hand, is getting a chance only if worker A is a low type. And even when he gets the chance, he gets it with some delay, which is captured by lambda over lambda plus r. This is essentially coming from discounting and from the time that it will take for worker A to generate a breakdown. Once worker B gets a chance, his payoff has a similar structure to that of worker A. As PB is approaching PA, this continuation payoff is converging to that of worker A. But of course, this first term, the factor that multiplies continuation payoff, is not converging to 1. In fact, it doesn't include a PB in there. So this, notice here that even if lambda is going to plus infinity, so even as the employer is learning very, very fast, this factor is still not converging to 1. It's converging to 1 minus PA, capturing the fact that worker B gets a chance only if worker A is a low type. So let me just summarize what we've seen. So we've argued that as PB goes to PA, worker A's advantage from early career discrimination vanishes under breakthrough learning, persists, and in fact it spirals under breakdown learning. So that's to say, in breakthrough environments, comparable workers are getting comparable lifetime payoffs, but that's not the case in breakdown environments. And especially, and what's perhaps even more surprising, it's not the case even as the employer learns very fast. So this is the basic contrast that the basic insight that we get from this baseline model. the rest of this talk will be about arguing that this is indeed a very robust observation. In particular, we explore the contrast in 3 directions. First, we ask what happens when there are many employers and many workers, potentially from groups of different sizes, and when wages are flexible, so potentially wages can fix, can correct dynamics in the market. I'll visit these 2 questions in the remaining of the talk. One sort of direction that we explore quite a bit in the paper, but that I won't have time to talk about today, is the opportunity that the workers might have to invest in their productivity. So think of this as potentially equal access to investment in productivity, being able to level the playing field for the 2 groups. We show there that the same contracts continues to go through. So investment in productivity does not hurt the self-correcting property of breakthrough environments, but it does in fact make inequality worse in breakdown environments. And this is a pretty robust observation because it holds across all investment equilibria there. Moreover, we have a few—
Ariana, I just wanted to tell you that you have 3 more minutes for your presentation.
Okay, thank you. So I just want to point out that we extend the contrast in a number of different directions, including inconclusive signals, misspecified beliefs, so inaccurate beliefs in Aislin's language, and potentially different speeds of learning for different groups. So in these very precious 3 minutes, let me just quickly give you an understanding of how we extend the baseline model to large markets and flexible wages. We assume a unit mass of tasks, an alpha mass of A workers, and a beta mass of B workers. We assume that matching is frictionless, so employers and workers are randomly meet each other and are matched frictionlessly, and the match happens if both of them accept the match. Crucially, we consider the case in which tasks are scarce. So that's to say, alpha plus beta is less than 1. There are more workers than tasks, so the employers will have to exclude some of the workers at the beginning from getting tasks. So our basic insight from this, so just to be clear, in this discussion right now, I'm still keeping wages fixed. And the basic insight that I've just given you from the baseline model continues to go through. Under breakthrough learning, it will still be the case that even though worker A workers will be favored at first, the delay that group B faces will vanish as PB goes to PA. So that's to say, at the beginning, in the limit, both A workers and B workers will be getting a chance. With breakdown learning, the employers will start with A workers, and they'll continue with those until they generate breakdowns. So by a similar intuition to what we got from the baseline model, it will be the case that B workers will get a chance only if sufficiently many A workers will realize breakdowns. And that delay will not vanish as PB goes to PA. Okay, so let me get to flexible wages. So the question is, if wages are flexible, should we see that the spiraling in the breakdown environment goes away? So is it the case that wages are an effective corrective tool in addressing spiraling? The answer that we give in short is that no, as long as wages are not non-negative. So the approach that we take, and there was quite a bit of discussion on this, so let me just tell you on the approach that we take to flexible wages. We take a cooperative approach to it. So we are basically looking for a stable matching in this dynamic environment, where a matching specifies both the employer and the worker that's being matched at any instant, but also wage for that match. We first characterize the set of stable stage game matchings, and for that we're adopting Shapley and Shubik. And then we show that repeating any of these stable stage game matchings is dynamically stable. And for dynamic stability, we adopt a notion from Ali and Liu a recent contribution to dynamic stability notions in matchings. The solution that we get has a strikingly simple form. So only the most productive workers will be matched at any time. There will be a history-dependent marginal belief, which we denote by PM here. Workers with belief above PM will be hired. Those with belief below PM will not be hired. And the wage for the matched workers will be linear. So in here, I'm showing I have belief in the x-axis, wage on the y-axis. The green plot here is showing exactly the wage schedule. So workers with belief below PM are getting 0, they're not being hired. Workers with belief above PM are being hired, and their wage is the additional surplus that they generate relative to the marginal worker. Notice here that the wage is convex. If in a static world, if we had two workers, PA and PB, one slightly above the marginal belief, the other slightly below, in a static world in which workers are matched only once, we should see that their payoffs are very similar. So the payoff of a worker with belief PA is very close to 0. But this is not the case when workers multiple times.
Mariana, I have to ask you to conclude, so we leave a little bit of room for Q&A, please.
Very good. So let me just say that this is not the case in dynamic matchings, and let me stop here with the conclusions.
Awesome, thank you. All right, let's open it up. Questions, please. Comments also, okay. So I have a question then. So if you, the example of jobs you were describing, like a breakdown job would be airline pilot. So the way airlines learn about their pilot skills is not let them fly until they crash the plane and then they're fired, right? And then another pilot gets a chance.
Yes. Yes, so in that baseline environment, we're considering really very, very stark cases in which there is a signal that is conclusive and that drops the belief all the way down to 0, and the employer would not would stop hiring the worker from that point on.
That's true for pilots as well. My point is that the arrival rate of the signal that a pilot is the crashing type is really low. So that, you know, the good pilots will have a crash probability of 0, and the bad pilots will have a crash probability of once in 100 years.
Yes, so perhaps what you have in mind is perhaps another sort of a model in which signals are inconclusive. So you see a mistake that a pilot made that's not perhaps as conclusive as a crash, but that indicates a low productivity pilot. So it indicates some sort of mistake that the pilot made. We are able to extend the contrast to inconclusive signals of that sort as well. So it doesn't need to take the very stark form of crashes or major scientific breakthroughs. We could potentially think of signals that are less informative than that, but that still suggests either one type or the other.
So the critical thing is whether over time the belief is going up or down, right?
Absolutely, yes.
And that it can be pretty darn inconclusive, and that's still true, right?
Yes, so it takes quite a bit of work to actually establish a contrast with inconclusive signals, given that the employer might not want to fire upon one breakdown, might wait for multiple of those signals to accumulate. But as Peter said, it's essentially whether the belief is over time going up or down in the absence of a signal that is determining the classification that we're offering.
So the breakdown situation probably, I mean, if you really take the breakdown versus breakthrough dichotomy, seems like breakdown situation is unlikely to, you know, to appear, right? In the sense that you could probably, there will be a lot of kind of professional training schools that will play the role of figuring out, exactly what is the type of the worker, right? So similar to what Lucas is saying, right? Pilots have to go through multiple rounds of certification before they can be put on the job that may have serious consequences if breakdown were to occur. But then, if jobs have, if learning is only in the form of breakthrough going up, right? Then once you meet some threshold, you can be put on the job. So I guess that's one. Yeah. So I don't know if you are willing to make an argument that the result from the breakthrough case may be the more relevant one, which is in the actual job market. In that case, your theory can be used as a way to explain small differences in initial productivity can have long-lasting consequences.
So I beg to differ here, actually. So Bose and Lang have a quite interesting sort of extension of or study of monitoring in guardian jobs, where they argue that perhaps the most common type of job that we see are jobs in which of a guardian nature, in which if the worker is making mistakes, then they're getting less and less likely to be kept in the position over time. I do agree with you that we could potentially have signaling, some sort of tests or interviews that we could build into this baseline model to capture training and screening stages at the beginning. And you could think of what we're arguing from the baseline model and on as the idea that if the same signal, if we have a test, let's say at the beginning at time 0, if the same signal is generated by two different or very similar signals are generated by two different groups, we should be observing a sharp contrast between these two learning environments. I think other types of guardian jobs that sort of might be familiar to us would be surgeons, routine surgeons. So Sarsens has an interesting study of differences between male and female surgeons and referrals. And there she tracks deaths as the outcome between surgeons. You could think of corporate board seats as another type of environment in which that give a long extended period to whoever is hired first. Assembly line is perhaps the classical example in that as well.
So I think one reason I was commenting on like the probability of the speed of breakdown events is because so you're working very hard to on the limit case, because that the limiting case and showing that the limiting discrimination persists in breakdown jobs but not in breakthrough jobs, because limiting results are impressive for economists and therefore get published better. But if you're just talking about explaining discrimination in the real world, I'm perfectly happy to accept your results on the non-limit results in the breakthrough jobs as well, because I mean, I would argue that the breakthroughs arrive at such a slow rate as well in many cases that, you know, if you ask me, for example, on like, all right, the arrival rates of breakthroughs measured as good publications for economics professors and the beliefs about the initial differences in skill distributions, I feel like those arrival rates are so slow and the belief differences are so big that I don't think we need to talk about a limiting case here, really. Like, that's how I would explain why there is discrimination in many breakthrough professions as well.
So thank you for bringing that up. So it's true, so perhaps I did not convey this during the talk, but it's true that our results also hold away from the limit case, right? So they're not knife edge in that sense. Why we find the limiting case particularly important and interesting is that it's showing that even as abilities between different groups, or even as productivities, access to education and so on are becoming massively accessible, we should still be seeing that some learning environments sort of magnify those initial differences in ways that we wouldn't potentially expect ex ante. So it's in a sense a pessimistic message on how social change can translate into equal chances for different groups in the labor market. But you're absolutely right that even though we're focusing on comparable social groups, and we think that that's what we see in many settings, for instance, Sarsens argues that the abilities of male and female surgeons are quite comparable, the distributions are quite comparable, we still agree that there are major obstacles other than the ones that were.
I'd love to talk more about this. It's a great paper. Thank you. But unfortunately, it's also time to move on. So, Yanku, you have a question?
I have one. Okay.
Well, how about this? We asked Teddy if he's okay with.
Sorry,
I'm sure he's okay.
Wearing the same hat as Teddy's. Let me not ask. Because Teddy is presenting our paper. So.
Well, it's your choice. And do you want to present? Do you want to ask your question?
It's just a quick question. I was thinking that, I kind of agree that the learning environment is specific to jobs, but it is, to some extent also endogenous, right? It's just depending on what kind of monitoring technology that you choose. Even in the surgeon examples, you could have like some stark outcome variable like death and mistakes, but you can also have more softer like information coming from peer reviews and whatnot. And so it's depending on, really it's up to what kind of monitoring investment that you make into the situation to determine what kind of learning environment you are in. So breakdown versus breakthrough, certainly one can imagine like, endogenously choosing what kind of environment you choose to be in as one possibility. And the second small question was that if you do adopt like an affirmative action in the breakdown environment, you might see complete reversal, spiraling in the opposite direction after some degree of affirmative action. And I'm wondering whether we see this kind of outcome in practice.
Thank you. So for the first question, absolutely, I agree that in many settings, the employer has the flexibility to design the monitoring strategy, so to speak. So here we're considering cases in which the learning environment is really intrinsic to the job, or perhaps the employer cannot adjust the learning environment very flexibly. So there will be perhaps some sort of norm in what learning environment is adopted within an industry and so on. We also have a small result that shows that the employer under certain conditions will prefer the breakdown environment to the breakthrough one. So at least in some cases that we know of, that will be the employer's preferred choice as well. As far as affirmative action goes, we actually have looked a little bit into temporary affirmative action. There are many sort of ways you can incorporate affirmative action in this setup. We've considered some of them, and the takeaway there is that even in breakdown environments, it really matters how you implement the affirmative action. How exactly do you mix between workers at the beginning, or for how long do you ask the employers to continue employing the discriminated group at the beginning, and so on. So we're so far we're staying silent on what are the clear-cut implications of different affirmative action policies. It's very interesting what you're saying about the potential reversal of spiraling. So far, at least, we've mostly looked at affirmative action policies that try to correct the spiraling in the breakdown environment.
All right, thank you very much. So our last speaker is Teddy Kim. He will present Statistical Discrimination and Ratings Guided Markets.
Right. So thank you very much for having me in this great workshop. This is joint work with Yanku Che at Columbia and Wei-Jie Zhong, who's starting at Stanford this year. And so Yanku is here and he's going to help me, but Wei-Jie couldn't join us today. So in case you wanna see us, so this is a picture that has all three of us. So me, Yanku, Wei-Jie, and also like Konrad Millendorf, who is another quarter of ours. And this was April 2019 when we got together in New York City to work. And it was good old days, and hopefully we can get it back soon. I guess not only for us, but for everybody. All right, so let me get started. All right, so the basic motivation for this paper is that ratings, as you see here, have become so prevalent and important, but we still seem to have not good understanding about their economic consequences. So of course, the basic role of ratings is to provide information about products and services, which by itself is not so, it's rather trivial. But the interesting part is that most ratings come from the real market transactions. So the relationship between ratings and markets is not a one-way, but a two-way interaction. So ratings guide market interactions and market transactions, but ratings also get updated through market transactions. And this transaction is what you want to study in this paper. So what do we do? So our first goal is to develop a simple conceptual framework to think about this interaction. Okay, so we want to have this basic framework. And then our second goal is to apply this framework to the issue of statistical discrimination. So why? If you think about it, this actually makes sense, because we have statistical discrimination because we don't have good enough information about individuals. So if there are ratings, good ratings about individuals, maybe we don't need to use the people's social identities to make inferences. So although this makes perfect sense, in this paper we show that there's more than that. And in fact, the previous intuition applies and ratings can indeed eliminate statistical discrimination if ratings are sufficiently precise. But if not, that is, if the ratings are informative, but not so much, then we actually show that ratings can actually generate statistical discrimination. So I will use next 25 minutes to explain exactly why and how this can happen. But the main mechanism is pretty simple. So let me try to give it here. So in short, it's exactly because of the interaction between markets and ratings. In particular, we have this feedback loop. So suppose that there are two groups, group 1 and group 2. And suppose that somehow ratings for group 1 are less accurate. So people somehow think that ratings for group 1 are less precise. Then buyers have less information for group 1, so they are going to trade less with group 1. But then there are less transactions for group 1, and this is going to make their ratings less informative. So we have this, the closed feedback loop, and this is the reason why the ratings can create the statistical discrimination. And you might think that, well, this sounds very much like Cote and Lowry, so of course there are some similarities at the high level, but there are several important differences. And one clear difference, which I'm going to explain today, is that unlike Cote and Lowry, where different groups coordinate on different equilibrium, we may have discrimination in our model even if there exists a unique symmetric equilibrium. So this says that what you have, the statistical discrimination in this paper is not just another coordination failure. Okay. Right. So let me completely skip the related literature given the time constraint. So today, for the next 24 minutes, first I'm going to introduce the basic colorblind framework. So this is going to be the basic framework to think about ratings. And then I'm going to extend the model to include different groups of sellers. And then I'm going to explain how discrimination or discriminatory equilibrium can arise in this environment. Okay. All right. So here is our baseline colorblind model. So time is continuous, and we are going to focus on the steady state equilibrium. So everything is going to be on steady state, and there are sellers or workers on one side, and there are buyers or firms on the other side. the measure of sellers is normalized to 1, or the measure of buyers is given by Q. So Q represents the total measure of buyers. And buyers are homogeneous, where each seller is either high type or low type at each point in time. Okay, so this type of a seller represents her productivity or the quality of her product. And importantly, these buyer types are not perfectly persistent. So they are going to change as a certain Poisson rate delta. So the low type is going to become the high type at rate delta, and the high type is also going to become the low type at delta. And this is what buyers care about, but they are not observable to buyers, but sellers' ratings are observable. So buyers are going to search for sellers based on the sellers' ratings. Okay, so for simplicity, we assume that there are only 2 ratings, good or bad. Okay, and so suppose a buyer is matched with a seller, then the buyer is going to get utility UH or UL depending on the seller's type, and the buyer is going to pay price P to the buyer is going to pay P to the seller. And here, so in this baseline model, we assume that the wage or the price is exactly given. We are going to also assume that the price is not so large, so that we have trade in equilibrium. Okay. All right. So this is the baseline environment, and here, as I said, when buyers are looking for sellers, searching for sellers, they condition on sellers' ratings. So search is guided by ratings. So this means that there are 2 submarkets, one with sellers with good rating, and the other with sellers with bad rating. So from now on, I'm going to just call this submarket D and submarket B. Okay. And the matching technology is a completely standard one. So we are going to assume that the matching function exhibits constant return to scale. So each seller's matching rate, psi lambda, psi, and each buyer's matching rate, phi, depend only on the ratio of buyers to sellers, so lambda. Okay, and so for most of our results, we only need some standard properties of these functions, but to obtain even more clear result, sometimes we are going to focus on this Cobb-Douglas matching function, so that a seller's matching rate is equal to lambda to the k, or the buyer's matching rate is equal to lambda to the k minus 1. And this is again, we are just using the standard properties of the matching function in the search literature. And this is matching technology, and our rating technology is also pretty simple. So essentially, at each transaction, each seller's rating is going to get corrected with a certain probability, alpha. So suppose that you have the high type, but you have bad rating. So this is wrong rating. Or you have the low type, but you have the good rating. So you still have the bad rating and the wrong rating. In this case, if you meet a buyer and you trade, then the buyer is going to update your rating with a certain probability. So with probability alpha, now you are going to get the correct rating. So if you're the high type, your rating is going to become good. If you're the low type, your rating is going to become B, bad. And with remaining probability 1 minus alpha, your rating is not going to change. If you had good rating in the first place, so you're the high type and you had good rating, or you are the low type but you have bad rating, well, nothing is going to change. So your rating is going to stay. Okay, and this rating technology can be summarized by this transition matrix, but this is not going to be so important for us. All right, so now we begin by characterizing the stage-state distribution. And so we use this Pij to denote the total measure of sellers with type I and rating J. So each seller is indexed by I and J. So I is the type, J is the rating. So then we have these 4 measures, PHG, PLG, PHB, and PLB. So there are these 4 measures. And so the first, so this figure describes the movements of sellers among these 4 measures. So first, So as I said, each seller becomes the other type at rate data. So we have exchanges between PhD and PLG. So these people, PhD, these people are going to move to PLG at this rate delta, and vice versa. We also have exchange between PHB and PLB. And because of transaction and also rating updating, we also have movements from PHB to PhD and from PLG to PLB. So this is the case of the upgrade. So your type is going to become from B to Z. And this is the case of downgrade. So your type is going to change from G to B. And so here you see that this is, so essentially the idea is that this is the rate at which you are going to meet a seller, meet a buyer, and then with probability alpha, your rating is going to change. Okay, and so we can in steady state we can just solve this system equations, and then this is the curve solutions for these measures, and these forms and these specific forms are not so important, but they allow us to calculate something very important, which is expected quality in each submarket. So mu Z is the expected quality, so the proportion of high type sellers in submarket Z, and mu B is the proportion of high type sellers in submarket B. So now here comes a very important observation, which is that this mu Z, the expected quality in submarket Z, is increasing in lambda Z, while this mu B, the expected quality in submarket B, is decreasing in lambda. So there's a simple intuition for this. So we are increasing lambda. That means that we are sending more buyers to each submarket. So if we send more buyers to a submarket, that means that each seller in that submarket is going to trade more often. So each seller is going to trade more often. That means that each seller's rating is going to get updated more frequently. So essentially, if you send more buyers into each submarket, you are creating more information in that submarket. But mu Z represents the proportion of sellers and high type sellers in submarket Z, while the mu B represents the proportion of high type sellers in submarket B. So if in these two submarkets, so the way this proportion changes is different. In submarket Z, now the information is becoming more precise. In that case, mu Z is going to get close to 1. So if mu Z is close to 1, that means that all the sellers in that submarket are high type. So that's the case where the information is perfect. While in submarket B, if information becomes more precise, this mu B is going to get closer to 0. So they are moving in opposite directions. And I mean, this is something very elementary in information economics, but this actually has very important implication for buyers' expected payoffs. And as you will see, this is going to drive all of our results of this paper. All right, so we can write down the buyer's expected payoffs this way. So for each submarket, so this is what we are doing. So in each submarket, let's send one buyer to the submarket. So this buyer's expected payoff, so flow expected payoff is simply the matching rate B times lambda times the expected payoff from each transaction. So in both submarkets, these are the buyer's expected payoffs, and they look the same, but the way they behave is very different. So again, so crucial observation is that UB, buyer's expected payoffs in submarket B, are monotone and always decreasing in lambda B, but UZ, buyer's expected payoffs in submarket Z, are not necessarily monotone. They may increase. Right. So in order to see this, so imagine that you are sending more buyers to each submarket. Okay. Right, and then we are thinking about the individual buyer's expected payoff. So if we are sending more buyers to each sub-market, they increase competition or congestion among buyers, which is always bad to each individual buyer. So this competition effect is going to always lower buyers' expected payoffs. But information effect is going, so there's another effect, which we call information effect. This actually works in opposite directions. So in sub-market B, again, you are sending more buyers. As I explained above, if you do that, then the mu B, the average quality is, expected quality is going to go down. This is bad to the buyers. While in sub-market Z, you send more buyers, then expected quality is going to actually increase. So mu Z is going up. So combining these two, it's clear that in sub-market B, buyers' expected payoffs are going to decrease in lambda, while mu Z, buyers' expected payoffs in sub-market Z may or may not decrease. So
Teddy, a clarifying question. The price is restricted to be the same in the two markets?
Again,
the price, the P.
Yes, P is the same. So that's the assumption we are making in the baseline model. Okay. As we discussed, so again, there are several ways to endogenize these prices. But suppose that we begin by just fixing prices in the sub-markets, but they are potentially different between these two sub-markets. It doesn't make any difference. So all of our results are going to go through as long as the price difference is not so large.
Okay.
Thank you. So this is the crucial observation, and here the real question is when UZ, buyer's expected payoff in sub-market Z, are going to monotone. And this is where we use the assumption of Cobb-Douglas matching function. So with Cobb-Douglas matching function, there exists this K lower bar, and if what you can show is that if K is less than this K lower bar, then competition effect is always dominate the information effect. So UZ is going to be monotone, as you see here. So as you see here, as you increase lambda Z, UZ is going to always decrease. Again, because competition effect dominates information effect. But if K is above K lower bar and between 1, then the information effect can dominate the information effect can dominate the competition effect. So we always have this interval over which an interior interval over which UZ, buyer's expected payoffs in sub-market Z, are actually increasing. So with Cobb-Douglas, this is what you get. So if K is above K lower bar, UZ is not monotone, and it always decreases first, increase then, and then eventually it decreases again. So this is the observation, and so you will see how we actually use this result to create the discrimination. And before we do it, again, let me characterize the symmetric market equilibrium. So in equilibrium, we have two equilibrium conditions. So the first one is the indifference condition. So there are two sub-markets, sub-market B and sub-market Z, and so you can actually show that in our model, it cannot be the case that trade occurs in only one sub-market. So trade either occurs in both markets or there's no trade. And we made an assumption so that trade occurs in equilibrium. So in equilibrium, where trade has to occur in both sub-markets, that means that buyers must be indifferent between the two sub-markets. So UB lambda B must be equal to UZ lambda Z. And we also have the second condition, which is it's kind of the market clearing condition. So the left-hand side is the total measure of buyers present in this market. So this you can interpret this as the supply of buyers. And the right-hand side is sort of the demand of buyers. So this PHG plus PLG is the total number of sellers with good rating. And if you multiply lambda G to do this, this means that this is the total measure of buyers you need in sub-market Z. And the second term is likewise, the second term is the total number of buyers you need in sub-market B. Then if you add this up, that's the total supply. And in equilibrium, this total supply must be equal to, total demand must be equal to total supply. So now, so what is the equilibrium? Well, we are looking for a pair of lambda Z and lambda B that satisfy these two conditions. Okay, so look at the first condition. It's kind of clear that they are inversely related. So there are two sub-markets. Suppose that you send more buyers to one sub-market, then you have less buyers for the other market. So that's why this is decreasing. Okay, so and also you can see that if lambda Z is very, very large, it's infinity, then essentially that means that you are sending all the buyers to one sub-market. Then in the other sub-market, lambda is going to be close to 0. So you can see that this line is going to converge to 0 as you increase lambda to infinity. Okay. Now looking at the first condition, so suppose that lambda Z is 0. So there are no buyers in one sub-market. Where for buyers to be indifferent between these two sub-markets, you also should not have any buyers in the other sub-market. So lambda B also needs to be equal to 0. And if you increase lambda Z, lambda B is going to be stay away from 1. So overall, it's going to look like this. Okay. So we are going to have this blue curve. So this blue curve represents the first equivalent condition. The red curve represents the second market creating condition. And so they are going to always have an intersection, and as usual, the intersection is going to give us an equilibrium. Okay, and this equilibrium may or may not be unique, and it depends. So if K is less than K lower bar, so again, below K lower bar, UZ is the monotone. So this means that this blue curve is going to be also monotone. Okay, then we can have only one intersection. So there exists a unique symmetric equilibrium. But if K is above K lower bar, then UZ is not monotone. So this blue curve is not going to be monotone anymore. Now we can have multiple intersections. So the figure you are looking at, there are 3 intersections. This means that there are 3 equilibrium. And in fact, this figure is also the case where K is above K lower bar. So this curve is not monotone. And even though this is not monotone, we still can have this unique equilibrium. Okay. So this is our basic framework, or you can say that this is characterization of the symmetric equilibrium. And now for the next 6 minutes, let me explain how we can actually generate discrimination within this framework. So we are going to introduce two groups of sellers denoted by L. So group 1 and group 2. So they are pair irrelevant, but they are perfectly persistent and also importantly observable. And just to highlight discrimination, we are going to assume that both groups have the same size, so 1/2 and 1/2. And now each seller is indexed by 3 variables: I, type, J, rating, and L, the group identity. Now, because J and L are observable, there are 4 submarkets. G1, so this is the sellers, group 1 sellers with good rating, and we also have B1, G2, and B2. So now we have four different submarkets, and now we need to think about this. And given what you have already, we can actually directly go to equilibrium. So in equilibrium, we know that buyers must be indifferent over all 4 different submarkets. So we need to have these equalities. So UZ lambda Z1 and UB lambda B1, UB lambda B2, and UZ lambda Z2 must be the same, all the same. Now, looking at the middle equality, we know that UB is monotone all the time. This means that lambda B1 must be equal to lambda B2. Okay, so this means that so there are the submarkets with bad ratings. In those 2 submarkets, the ratio of buyers to sellers must be the same. So, and there's an intuition for this, but let me skip. And so this implies that for discrimination, for us to have discrimination, it must be the case that there are 2 different values of lambda Z. So lambda Z1 must be different from lambda Z2. but they must give the same payoff to buyers. Okay, and so what is this? Well, this is exactly the non-monotonicity of UZ. Okay, so if you can find this pair of lambda G1 and lambda G2 if and only if UZ is non-monotone. And we already know a lot about monotonicity of UZ. So again, if K is less than K lower bar, then this UZ is monotone. In this case, we don't have discrimination. So we cannot have any asymmetric equilibrium. So there's no discrimination. But if K is above K lower bar, then well, you can actually construct an asymmetric equilibrium, a discriminatory equilibrium. And so to explain this part better, so let me show you exactly and explicitly how we can construct an asymmetric equilibrium. So fix any K, which is above K lower bar, then this blue curve, so this buyer indifference curve is going to have this shape. So it goes up first, decreases, and then goes up. Then pick any lambda B between this dip and this peak. So between lambda lower bar B and lambda upper bar B. Then there are three corresponding values of lambda Z, and then pick any two. So here, let's say this point and this point, lambda G1 and lambda G2. Okay. Then by construction, buyers are indifferent over all the four different submarkets. So we pick these lambdas so that buyers are indifferent. So the only thing we need is to have this Q to satisfy the market clearing condition. And now notice that we can do this construction for any value of lambda B in this interval, and you can also do this for any pair of lambda J's. So this means that, well, for each K, which is above K lower bar, there exists an interval over which, as such that an asymmetric equilibrium or a discriminatory equilibrium exists if and only if Q belongs to that interval. Okay, and so one thing is that you can do this whenever K is above K lower bar. So this means that a discriminatory equilibrium can exist even if there is a unique symmetric equilibrium.
Teddy, you have 3 minutes.
Yes, I'll finish in time. All right. By the way, so this is the discriminatory outcome. So we began with two identical groups, and we are seeing that they can be treated differently by markets. And here, this discrimination also has the real payoff consequences in the sense that if lambda G1 is less than lambda G2, then group 1 sellers' expected payoffs are strictly smaller than the group 2 sellers' expected payoffs. So you can actually show this easily. And for the next 2 minutes, let me just introduce two other results of ours. So the first one is stability, and so we use the standard stability concept. So the idea is that there are two groups. Suppose that we move a small measure of buyers from one group to the other and see whether these buyers want to go back to the original group. Okay, that's our stability concept. If you apply that, what you can show is that, or there's a sense in which asymmetric equilibrium is more stable than symmetric equilibrium. So there's a lot, but our claim is that suppose that we have both symmetric equilibrium and asymmetric equilibrium, then this symmetric equilibrium may or may not be stable, but either this asymmetric equilibrium is stable or there exists another asymmetric equilibrium that is stable. So that's our claim. And so I don't have enough time to explain the details. And our last result is about the rating quality. So what this result is saying is that a discrimination can arise if and only if rating quality belongs to a certain intermediate range. So meaning that if rating quality is very low or rating quality is very good, then we don't have the possibility of discrimination. So this implies that, so suppose that there's a discrimination, and suppose that it's coming from ratings, then you can solve the problem either by just getting rid of ratings or just by making ratings even more effective. So that's another way to solve this, the problem of discrimination. And so our work is not complete. So we are thinking about, in particular, this, the different kinds of policies like affirmative action and also algorithm-based policies. So we are still working on this. And this is all. So thank you very much.
Can I ask a question? So I was wondering, compared to like, what is the efficient allocation of consumers across these two submarkets, and then compared to the efficient allocation, which submarket has more over sort of, have too many consumers, or too little consumers? A
great question. We actually don't have a characterization for the efficient outcome. So there are actually several things going on. So there are several kinds of externalities going on here. So like there's a typical congestion externality, but we also have the information externality. So at least according to our numerical examples, it can actually go either way. So like, turns out that characterization of efficient outcome is pretty complicated. And so, I mean, that's also like, so by the way, if you look at the baseline framework, we don't know exactly how the efficient outcome, works. And that implies that we also can't tell whether the discriminatory equilibrium is actually necessarily bad. So it can be actually more efficient than symmetric outcome, but that's actually something we also need to think more about. And what was your second part?
Oh, it's related. I was wondering if we have an idea about the efficient allocation, then maybe we know which market has too many consumers, which market has too few consumers. Yeah.
So we also, that's actually a part of the questions we actually want to address with this. So that's like affirmative action, like where you want to, so where you want to send more buyers, relatively more buyers, to which group, right? And so it looks like
I thought there's just one choice of the planner, which is just to allocate a fraction of consumers that goes to market 1, market 2.
Yes,
so
yes. So that's exactly what. So we don't have the full analytical result, but looks like when one group is discriminated against, it helps this group if you send more buyers. So that's not so surprising. And in fact, I think that more interesting. So because we are thinking about these ratings, I think another policy you can think of is this so-called algorithm-based policy. So here, what you are trying to do is to change these probabilities of upgrade or downgrade. So suppose that there's one group and this group is being treated like badly, then you want to help this group, okay? But the question is exactly how. Do you want them to get good rating easily, or do you want to make it harder for them to be downgraded? So that's the kind of question we want to ask. And so according to some numerical research, looks like it can actually go either way. So trying to help this group can actually backfire. So if you make them to get the good rating with higher probability than the other group, that group actually that group's expected payoff and the welfare can actually go down. So that's but again, we don't actually have a complete picture about the effect of all these policies.
Thank you.
We have a question from the audience. If it's okay that I take that.
Let me check. So,
Bruno, that's you.
Hi. That's a great talk. I have a question related to the stability concept you use. I was wondering if this would imply a different form of robustness. That say there was an epsilon probability that somebody that actually get a bad review based completely on preference-based discrimination, and then you think this epsilon probability can go to 0. Would that like also eliminate the symmetric equilibrium? Because I think that would be an argument that more in place, like with this idea that, well, maybe there are very few people there that are actually discriminating against a group, but that's enough to make big movements on the outcomes.
So we haven't thought about that robustness. So again, our stability concept was about just moving buyers, but I think you are right that we can actually also think about robustness in terms of the ratings, right? So this is what.
So I didn't get the notion that, I mean, I don't know who is, I'm not seeing the,
So
who is this? So can you repeat this proposed notion of robustness?
yeah, so the way I was thinking is that, say there is a group that with some probability gets a bad review, even if they are high quality, and call that a preference-based discrimination. They just get a bad review because some people don't like them. And think about what would be the equilibriums when this epsilon probability of getting this preference-based rating goes to 0. And my question would feels like the symmetric equilibrium will not be the limit, but I might be wrong about that. I don't.
But that's actually related to, so that actually requires to do the non-steady state analysis. So like in some sense, there's say that there's a steady state equilibrium, right? So what you're suggesting is that suppose that somehow we change this steady state distribution, right? So then let's see whether where the market is going, which equilibrium the market is going to converge to. So I think that's that's one. There could be a way to answer your question, but we haven't been able to actually do this non-stationary analysis.
I'm also wondering whether this kind of perturbation, if you will, may correspond to the perturbation that we are considering in some way. Because if there is some preference-based discrimination or mistake in the ratings, which is not correctly recognized by everybody. So people are a bit mistaken about ratings that actually are coming from some sort of inherent discrimination rather than accurate information. So there is a misinterpretation of rating, which may put the equilibrium away from the true equilibrium that would arise if everybody were correctly aware of the structure and updating correctly. And if you allow the market to adjust itself, maybe, the question is whether that kind of puts the equilibrium shift, the system away from the original equilibrium that we are perturbing or not. So maybe I'm thinking maybe there is some connection between that sort of perturbation and the kind of perturbation that we've been thinking.
Thank you for the question.
Yeah, no, thanks for that.
Everybody, I just want to use the opportunity that we're out of our official time to say thank you to everybody who stayed on this long. And well, now we can keep talking.
Thank you.
So thank you, organizers.
Thank you, Lucas, for
This is a great workshop.
Thank you for joining the workshop.
Thanks.
We can keep chatting. That's all okay. You can also go.
Teddy, nice talk. Just one.
Thank you very much.
So you said the prices for